Right now, at this moment, you might be trapped inside the most massive prison in existence. Not a cell with bars, not a planet with gravity, a black hole. Evidence from the James Webb Space Telescope shows galaxies spinning in patterns that should not exist. Calculations reveal our universe's size perfectly matches what you would find inside a collapsed star. Physicists from Barcelona to Princeton have proven the math works. The Big Bang might have been a bounce inside something far larger. If you enjoy unraveling cosmic mysteries, hit subscribe. What comes next will change how you see everything. Prepare yourselves. We begin. Picture a sphere containing everything you can see. Every star, every galaxy, every particle of light that has reached Earth in nearly 14 billion years. Now compress all that mass into a single point and calculate how large a black hole it would create. The answer should terrify you. The radius matches perfectly. When Karl Schwarzschild solved Einstein's equations in 1916, he discovered something disturbing. Any mass compressed within a specific radius becomes a black hole. That radius depends only on how much mass you have. More mass means a larger radius, but the relationship follows a simple rule. Double the mass, and you double the radius. This is confirmed physics, tested thousands of times. Scientists have measured our observable universe. They know its mass. They know its radius. When you plug those numbers into Schwarzschild's equation, something impossible happens. The universe's actual radius equals the radius at which all its mass would form a black hole's event horizon. This is not an approximation. The numbers align within measurement error. Most physicists dismiss this as coincidence. They argue the universe expands differently than black holes collapse. They point out there is no outside for our universe to be a black hole inside of. They remind us that black holes trap everything while our cosmos continues expanding. These are fair arguments. They sound reasonable. They might even be correct. But the mathematics does not care about reasonable. Theoretical physicist Raj Pathria published his concerns in Nature back in 1972. He calculated that our universe could be confined within a black hole boundary, even while appearing to expand from inside. His paper received little attention. Scientists had just begun understanding black holes themselves. The idea seemed too strange, too disconnected from observation. The community moved on, yet the calculation remained. Decades passed, and our measurements improved. We mapped the cosmic microwave background. We counted galaxies billions of light years away. We measured the universe's expansion rate with increasing precision. Every new observation confirmed the same disturbing relationship. Our universe sits exactly at the threshold where it should become a black hole. Here is what makes this genuinely unsettling. Black holes scale with mass in a peculiar way. Small black holes are incredibly dense. They pack multiple stellar masses into spaces smaller than cities. But supermassive black holes spread their mass across vast regions. A black hole containing our universe's mass would have roughly the same average density we observe around us. The density of a few hydrogen atoms per cubic meter. You would not notice the difference from inside. Physicist Sean Carroll argues this means nothing. He points out that spatially flat universes always show this relationship. The Friedmann equation predicts it naturally. If the universe has zero curvature, which observations suggest, then the Schwarzschild radius will equal the Hubble length. Simple geometry, nothing more. Others disagree. They see a pattern too perfect to ignore. Why would our universe exist precisely at this boundary? Why would the cosmos expand at exactly escape velocity from itself? The questions multiply faster than answers. But what astronomers discovered in 2025 makes everything more complicated. Far more complicated. His solution. Einstein's field equations permitted a rotating universe, not galaxies rotating within space, but space itself turning like a cosmic merry-go-round. This was not speculation. Gödel had found an exact mathematical solution that satisfied every requirement of general relativity. The implications were disturbing. In Gödel's rotating universe, you could travel in a large enough circle and return to your own past. not through wormholes or exotic matter, just by moving through ordinary space on a specific path. The mathematics allowed closed time-like curves, loops in space-time where cause and effect chase each other endlessly. You could shake hands with yourself before you left. Einstein hated it. He recognized the solution was mathematically valid, but argued it must be physically forbidden. Something had to prevent this. General relativity could not permit time travel to the past. The universe could not rotate this way. Reality had to obey causality. But Gödel had proven otherwise. General relativity, the theory Einstein trusted to describe all of space-time, was perfectly comfortable with time loops. The equations did not care about philosophical objections. They simply described what could exist. This posed a profound problem. If general relativity allows time travel, then either the theory is incomplete, or time itself works differently than we assume. Gödel believed he had exposed a fatal flaw. Time, he argued, might not be real at all, just an illusion created by observers moving through a static four-dimensional geometry. Scientists immediately looked for rotation in our actual universe. They measured light from distant galaxies. They analyzed the cosmic microwave background. They searched for any sign that space itself spins. Observations found nothing. If our universe rotates, it does so at less than 1/10 quadrillionth of a degree per century, effectively zero. Gödel's universe seemed like a mathematical curiosity, an interesting theoretical dead end with no connection to reality. Physicists moved on to problems with observational consequences. The rotating cosmos joined the pile of solutions that satisfied equations but described nothing real. Then the James Webb Space Telescope began operating in 2021. Its unprecedented resolution captured galaxies from when the universe was young. Astronomers analyzed their shapes, measuring how they spin. They expected random distribution, half clockwise, half counterclockwise, pure cosmic chaos. They found something else entirely. Computer scientist Lior Shamir analyzed 263 galaxies in the telescope's Advanced Deep Extragalactic Survey. The images were clear enough that anyone could see the pattern without specialized training. Approximately 2/3 rotated in the same direction relative to our Milky Way. Only 1/3 spun the opposite way. This should not happen in a random universe. The probability of such asymmetry appearing by chance drops to essentially zero. Either something is wrong with how we measure galaxy rotation, or the cosmos has a preferred direction, a memory of how it began, an axis inherited from something deeper. Shamir published his findings in monthly notices of the Royal Astronomical Society in early 2025. He offered two explanations. First, the universe might have been born rotating, exactly as Gödel's mathematics allowed. Second, our measurements might be skewed by Earth's motion through space in ways we have not accounted for. Both possibilities are disturbing. Both suggest our understanding is incomplete, and both point towards something stranger lurking beneath the surface. Because if the universe inherited its rotation from somewhere, that somewhere might be the black hole we are trapped inside. Chapter 3. Two boundaries that shouldn't exist. Every black hole has an event horizon, an invisible surface marking the point of no return. Cross that boundary and the universe changes. Not gradually, not gently, absolutely. Inside the horizon, escape becomes impossible. Not difficult, not unlikely. Geometrically forbidden by the structure of space-time itself, all paths lead inward toward the singularity. Future directions point only to increasing density and eventual destruction. Light cannot climb back out. Information cannot leave. The interior becomes disconnected from the rest of reality. This is confirmed science. We have photographed event horizons around supermassive black holes. The Event Horizon Telescope captured the glowing ring of matter swirling around the darkness at our galaxy's center. That darkness is not empty space. It is a region from which no light escapes. A boundary in space-time. Now consider our universe. We also have a horizon, the cosmological horizon. Light travels at a fixed speed. The universe has a finite age. Therefore, light from sufficiently distant regions has not had time to reach us yet. There exists a sphere around Earth, beyond which we cannot see. Not because our telescopes are inadequate, not because objects are too faint, because the light simply has not arrived. This creates an effective boundary. We can see roughly 46 billion light-years in every direction, even though the universe is only 13.8 billion years old. Expansion stretched those early photons during their journey, but a limit remains. Beyond our cosmological horizon, events happen that can never affect us, information that can never reach our telescopes, a disconnection from the rest of reality, two boundaries, both creating regions we cannot observe, both fundamentally limiting what we can know, both described by the geometry of space-time rather than the absence of matter. The similarities are not coincidental. Both horizons emerge from the same underlying physics. Both represent surfaces where light becomes trapped relative to an observer. In a black hole, gravity prevents light from escaping outward. In our universe, expansion prevents light from reaching us from beyond a certain distance. Physicist Leonard Susskind has argued they might be exactly the same thing viewed from different perspectives. What we call our cosmological horizon could be an event horizon, seen from inside. What we interpret as cosmic expansion could be the geometry of space-time inside a black hole. We simply cannot tell the difference because we have never been on both sides of such a boundary to compare. This idea, called the holographic principle, suggests even more. Information about the volume of space might be encoded on its boundary surface. Three-dimensional reality could be a projection from a two-dimensional horizon. The universe inside a black hole would contain exactly as much information as can be written on its event horizon. Mathematical physicist Gerard Hooft developed this concept in the 1970s. He showed that black hole entropy depends on surface area, not volume. A black hole with twice the radius has 4 times the entropy, following area scaling. This suggested something profound about how information works at the boundary of space-time. If our universe is inside a black hole, then everything we experience could be described by information on a distant surface. Reality would be a hologram. 3 dimensions would be an illusion created by projecting from 2. Depth would be manufactured by the physics of the boundary. This is a theory, not confirmed fact, but it offers one way to understand why both boundaries behave so similarly. They are the same structure viewed from different angles, one trapping light inside, the other preventing light from entering, both creating regions causally disconnected from their surroundings. The question becomes whether these similarities reveal something true about the universe's nature, or whether they are simply accidents of mathematics, 2 different phenomena that happen to share geometric properties without deeper connection. But there is more evidence. Evidence involving the one feature black holes and universes definitely share, a beginning marked by impossible density. Chapter 4. The Singularity Problem. At the center of every black hole, general relativity predicts a singularity, a point where density becomes infinite, where space-time curvature grows without bound, where the equations produce meaningless results and physics breaks down completely. This is not hyperbole. When you follow the mathematics of gravitational collapse to its conclusion, you reach a location where matter is compressed to 0 volume. Density equals mass divided by volume. 0 in the denominator means infinite density. The calculation produces infinity, which in physics means the theory has failed. Confirmed observations support this. We see stars collapse when they exhaust their fuel. If the core exceeds about 3 stellar masses, nothing can stop the crush. Neutron degeneracy pressure fails. The core contracts past its Schwarzschild radius. An event horizon forms. Everything inside continues falling inward. The mathematics offers no escape, no force strong enough to halt the collapse. Only a singularity remains at the end. Now rewind the universe's history. Trace cosmic expansion backward in time. Galaxies move closer together. Temperature increases. Density rises. Keep going back and you reach a moment when everything occupied the same point. Infinite density, infinite temperature, 0 volume, We call it the Big Bang, another singularity. Physicist Roger Penrose and Stephen Hawking proved in the 1960s that singularities are inevitable in general relativity. Their theorems showed that under reasonable conditions, gravitational collapse must produce infinite density, not might, not probably, must. The mathematics leaves no alternative. This creates a profound problem. Physics cannot describe infinities. Equations that produce infinite answers are broken. They tell us the theory has reached its limit. Something fundamental is missing from our understanding. General relativity works beautifully for normal spacetime but fails at extreme conditions. Most physicists believe quantum mechanics solves this. At incredibly small scales, quantum effects should prevent infinite compression. The uncertainty principle might provide pressure that halts collapse before reaching true zero volume. Quantum gravity, when we finally develop that theory, will probably show that singularities are not real, just artifacts of using classical equations where quantum effects dominate. But we have no quantum theory of gravity yet. We can write down ideas, but we cannot calculate reliably what happens at these extremes. The singularity problem remains unsolved. A gap in our knowledge sitting at the most important moment in cosmic history and at the heart of every black hole. Here is what makes this particularly unsettling. The singularity inside a black hole and the singularity at the Big Bang have identical mathematical structure. Both arise from the same equations. Both represent the same kind of breakdown. Both indicate the same missing physics. What if they are not just similar? What if they are actually the same thing? In 1972, physicist Raj Pathria suggested exactly this. The Big Bang singularity could be the singularity inside a black hole, not similar to one, not like one. Actually, genuinely, the same object. Our universe would then be the interior of a black hole that collapsed in some larger parent universe. From outside, observers would see a black hole form and settle into a stable state. Nothing unusual. Just another collapsed star. But inside, beyond the event horizon, the geometry would be completely different. Space-time would expand, temperature would drop, matter would spread out. An entire universe would emerge from what looks like a point from outside. This solves the singularity problem in an unexpected way. There is no singularity, never was. The mathematics of collapse and expansion connect smoothly if you account for the boundary conditions properly. What appears to be infinite density from one perspective is just a moment of maximum compression from another. The universe bounces. Density reaches an extreme but finite value, then reverses direction. Polish physicist Nikodem Poplawski worked out the details. His calculations showed that if you include torsion, a geometric property that general relativity usually ignores, the bounce happens naturally. Quantum mechanics combined with rotating matter creates repulsive forces at extremely high density. The collapse halts. Everything rebounds outward. What emerges is indistinguishable from our universe. Same expansion rate, same temperature history, same structure formation. You cannot tell from inside whether you are living in a conventional Big Bang cosmos or inside a black hole that bounced. The mathematics work, the physics check out, the theory makes predictions we can potentially test. But it requires accepting something that feels impossible, that we are not living in the universe. We are living inside something else entirely. Chapter 5. A Universe Born Spinning. The James Webb Space Telescope cost $10 billion and took 30 years to build. It launched in December 2021 and stationed itself nearly 1 million miles from Earth. Its mirror spans over 21 feet across and can detect infrared light from the universe's first galaxies. When it began sending data back, astronomers expected surprises. They got one they were not prepared for. Lior Shamir studies galaxy shapes using computer algorithms. His specialty is analyzing how spiral galaxies rotate by examining their structure, clockwise or counterclockwise. A simple question with a straightforward answer for any individual galaxy. But patterns across many galaxies reveal something about the universe itself. If the cosmos is random and isotropic, meaning it looks the same in all directions, then galaxy rotation should be random too. 50% spinning one way, 50% the other way. Flip a coin 1,000,000 times and you get roughly equal heads and tails. Physics offers no reason for a preferred direction. Shamir analyzed 263 galaxies captured by the James Webb Advanced Deep Extragalactic Survey. The field sits near the galactic pole, looking away from the plane of the Milky Way where dust might obscure distant objects. The galaxies are ancient, their light traveling for billions of years before reaching our telescopes, clear enough to see spiral arms, distinct enough to determine rotation direction without ambiguity. Approximately 2/3 rotate clockwise when viewed from Earth. Only 1/3 rotate counterclockwise. Shamir published his results in monthly notices of the Royal Astronomical Society in February 2025. He emphasized that the difference is so obvious that anyone looking at the images can see it. No special skills required. No complex analysis necessary. Mathematics predicted 76 years ago. Space-time itself could spin. Not the galaxies rotating within space, but space carrying galaxies along as it turns. This would create a preferred direction everywhere. Galaxies would inherit their rotation from the geometry of the universe itself. We would see asymmetry because the cosmos has an axis. This explanation agrees with black hole cosmology. If our universe formed inside a rotating black hole, it would inherit angular momentum from the collapse that created it. Physicist Nikodem Poplovsky has argued that the spinning black hole from a parent universe would leave exactly this kind of signature. Galaxies should show preferred rotation, matching the black hole's spin axis. The problem is that cosmic rotation contradicts decades of observations. Measurements of the cosmic microwave background show no sign of universal spin. Studies of distant quasars find no systematic bias. If the universe rotates, it does so incredibly slowly. Too slowly to create the galaxy patterns Webb observes. Second possibility, our measurements are wrong. Not the telescope, not the analysis, but our understanding of how Earth's motion through space affects what we see. The Milky Way rotates around its center. That center orbits within our local group of galaxies. The local group moves relative to the cosmic microwave background at over 600 kilometers per second. All this motion creates Doppler effects. Galaxies moving away appear redder and dimmer. Galaxies approaching appear bluer and brighter. If galaxies rotating one direction systematically appear brighter than those rotating the other way, telescopes would preferentially detect them. We would see more of one type simply because they are easier to photograph. The asymmetry would be an observational artifact, not a real feature of the cosmos. Shamir suggests this possibility requires recalibrating how we measure distances in deep space. If the Milky Way's rotation affects our observations more than previously thought, then our entire cosmic distance ladder might be wrong. Galaxy distances could be systematically over or underestimated. This would explain several unsolved problems in cosmology, including why measurements of cosmic expansion produce conflicting results. Both explanations lead somewhere uncomfortable. Either the universe spins, which means current cosmology is incomplete, or our distance measurements are fundamentally flawed, which also means current cosmology is incomplete. But the rotation pattern offers another clue, one that connects directly to the black hole hypothesis. Because galaxies farther from Earth show stronger asymmetry, the effect increases with distance. As if looking deeper into the past reveals the universe's rotation more clearly, as if the cosmos spun faster early in its history and has been slowing down as it expands. Exactly what you would expect if space-time inherited angular momentum from a collapsing black hole. Chapter 6. The Scientist Who Mapped the Impossible. Nikodem Poplovsky teaches physics at the University of New Haven in Connecticut. His office probably looks unremarkable. Shelves of textbooks, a computer, papers stacked in organized chaos. But the mathematics written on those papers describes something that should not exist. A universe without a singularity. Poplawski did not set out to prove we live in a black hole. He was studying Einstein-Cartan theory, an extension of general relativity developed in the 1920s. Standard relativity describes gravity as the curvature of space-time caused by mass and energy. Einstein-Cartan theory adds another geometric property called torsion, the twisting of space-time caused by spinning matter. In ordinary relativity, particles move along curved paths called geodesics, like balls rolling on a warped rubber sheet. Mass bends the sheet and particles follow the curves. Simple and elegant. But this picture ignores something fundamental about particles. They spin, electrons spin, protons spin, neutrons spin. Every fundamental particle has intrinsic angular momentum, not rotation like a planet turning on its axis, but a quantum property without classical equivalent. Point particles that somehow possess spin. In flat spacetime, particle spin does not matter much. It creates tiny magnetic fields but does not significantly affect motion. But in strongly curved spacetime, near black hole singularities, or at the Big Bang, spin becomes crucial. The geometry has to account for it, and when you include spin properly, you get torsion. Poplawski worked out what torsion does at extreme densities. The calculations were published in Physical Review D in 2012. His key insight came from understanding how torsion couples to spin. When matter reaches incredibly high density, fermions, the particles that make up atoms, cannot occupy the same quantum state. The Pauli exclusion principle forbids it. Two electrons cannot have identical properties in the same location. This exclusion creates pressure, not thermal pressure from heat, not degeneracy pressure from quantum uncertainty, a fundamentally new kind of repulsion arising from the geometry of spacetime itself. Torsion generates a force that pushes particles apart when they get too close. At normal densities, this force is negligible, invisible. But as matter collapses toward a singularity, as density approaches nuclear saturation and beyond, torsion pressure grows rapidly. It acts like a spring. Compress it further, and it pushes back harder. There comes a point where the repulsive force from torsion exceeds the attractive force of gravity. The collapse stops, then reverses. Poplawski calls this the big bounce. Instead of crushing to infinite density, matter reaches a maximum compression and rebounds. The singularity never forms. Density peaks at an enormous but finite value, roughly 100 million times nuclear density. Then space-time expands explosively in the opposite direction. This bounce creates what we observe as the Big Bang. Not a beginning from nothing, not creation ex nihilo, just a reversal of gravitational collapse, like a supernova explosion, except on cosmic scales. The universe bounces like a collapsing star bounces before exploding outward. Here is the remarkable part. From outside, observers see a black hole form normally. The event horizon appears. Matter disappears inside. Nothing unusual happens. But inside the event horizon, beyond the point where light cannot escape, the geometry is completely different. Time and space exchange roles. What outside observers interpret as the future becomes another direction in space inside. The singularity they expect at the center becomes a moment in time, the Big Bang moment. The mathematics work perfectly. Poplawski published solution after solution, showing the bounce occurs naturally in Einstein-Cartan gravity. No exotic matter required, no violations of known physics, just the logical consequence of including spin in the equations. His papers appeared in prestigious journals, Physics Letters B, General Relativity and Gravitation, the Astrophysical Journal. Other physicists checked his calculations. The math was sound. The theory made testable predictions. It solved genuine problems with the standard cosmological model. Yet most scientists ignored it, not because it was wrong, because it was too strange, too different from conventional thinking. The idea that our universe exists inside a black hole felt more like science fiction than science, easier to dismiss than to seriously consider. Poplawski did not stop. He calculated what happens to matter during the bounce, how density changes, how temperature evolves, how quantum effects manifest at these extremes. Every prediction matched what we observe: the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies. All of it emerged naturally from the bounce scenario. In 2010, he published a paper showing that if our universe formed this way, every black hole in our universe should create baby universes inside themselves. New expanding regions of space-time beyond each event horizon, universes within universes, nested like Russian dolls, each one inheriting slightly modified physics from its parent. A cosmic reproduction process driven by gravity and quantum mechanics. National Geographic and Science magazine listed this among the top 10 discoveries of 2010. Not confirmed discoveries, theoretical possibilities worth attention. The idea that black holes birth universes captured imaginations. It suggested an answer to why the universe exists at all. Not creation from nothing, but an eternal cycle of collapse and expansion. No beginning, no end, just transitions. And if true, it means something profound. When you look at the night sky, every black hole you observe is not an ending. It is the beginning of an entire cosmos emerging on the other side of physics. Chapter 7. What torsion actually does. Standard general relativity uses a mathematical object called the affine connection to describe how particles move through curved spacetime. This connection has a specific property. It is symmetric. Swapping two of its indices gives the same result. This symmetry makes calculations cleaner, but also makes an assumption that spacetime has no intrinsic twist. Einstein-Cartan theory removes that assumption. The connection becomes asymmetric. Its antisymmetric part is called the torsion tensor. Torsion represents how spacetime itself twists in response to spinning matter, just as curvature represents how spacetime bends in response to mass. Think of curvature like hills and valleys on a landscape. Balls roll downhill, following geodesics created by the terrain's shape. Torsion is different. Imagine the landscape itself spinning beneath your feet. The ground twists as you walk. Your path curves not just from hills, but from rotation in the surface itself. For ordinary matter at normal densities, torsion is negligible. The effect is real but tiny, about 1 part in 10 to the 69th power, completely unmeasurable with any current technology. This is why standard relativity works so well. Ignoring torsion introduces errors smaller than measurement precision for everything we have observed. Until you reach extreme conditions, when matter compresses to densities approaching nuclear saturation, roughly 1 quadrillion kilograms per cubic meter, particle spins begin to matter. The collective angular momentum of all those spinning fermions creates significant torsion. The spacetime twist becomes large enough to generate forces comparable to gravity. These forces are repulsive. Torsion pushes particles apart. The mechanism is subtle but powerful. In curved spacetime with torsion, fermions become spatially extended rather than point-like. They occupy a minimum volume determined by the Cartan length, about 100 million Planck lengths. Two fermions cannot occupy the same quantum state, which means they cannot overlap in space when torsion is significant. This creates an effective pressure, not from thermal motion, not from quantum uncertainty, from the geometric structure of spacetime, forbidding particles to compress beyond a certain limit. The Pauli exclusion principle, operating through the torsion connection, prevents infinite density. Nikodem Poplavsky calculated what happens when a collapsing cloud of matter reaches this critical density. The torsion force grows rapidly. It scales with density squared, meaning doubling density quadruples the force. Gravity also increases with density, but more slowly. There exists a crossover point where torsion repulsion exceeds gravitational attraction. At that moment, collapse halts. The cloud reaches minimum volume. Then spacetime geometry forces expansion. The bounce is not a choice, not a possibility, an inevitable consequence of the field equations. Einstein-Cartan gravity forbids singularities. They cannot form because torsion prevents the final stage of compression. The numbers are staggering. At the bounce, density reaches approximately 10 to the 96th kilograms per cubic meter, about 100 million times the density of atomic nuclei. Temperature exceeds 10 to the 32nd Kelvin. Energy density surpasses the Planck energy by orders of magnitude, yet the equations remain valid. Space-time behaves classically, even at these extremes. Recent observations of high-energy photons from gamma-ray bursts suggest this might be true. Physics does not break down at Planck scales the way many theories predicted. Classical geometry continues working at energies far beyond where quantum gravity was thought to become essential. If correct, this resolves one of physics' deepest problems. General relativity predicts its own failure at singularities. The equations produce infinities, which means they have reached their limit. Physicists expected quantum gravity to rescue the theory. Torsion offers an alternative. Include the full geometry of space-time, not just the symmetric part, and singularities never form. General relativity is complete after all. The bounce also explains cosmic inflation naturally. Standard cosmology requires an inflaton field, a hypothetical entity that has never been observed. This field supposedly drove exponential expansion in the first fraction of a second after the Big Bang. But where did the inflaton come from? What turned it on? What turned it off? The theory provides no answers. In the bounce scenario, rapid expansion occurs automatically. The torsion force that halted collapse continues pushing outward. Space-time expands exponentially for a brief period as the universe rebounds from maximum compression. No new fields required. No fine-tuned parameters. Just the dynamics of collapsing and expanding geometry. Dark energy becomes equally natural. The bounce does not happen instantaneously. There is a transition period where space-time geometry shifts from collapsing to expanding. This transition leaves residual torsion that decays slowly over billions of years. The decaying torsion acts like dark energy, accelerating cosmic expansion at late times. One force, two phases, inflation and dark energy unified through the physics of the bounce. The mathematics predict both without adding new components. The timeline matches observations. The expansion rates fit measurements. Everything works. But accepting this means accepting that we emerged from inside a black hole, that the Big Bang was not a beginning but a transition, that singularities, the monsters lurking at the end of gravitational collapse, are illusions created by incomplete equations, and that every black hole we observe creates universes we can never see. Chapter 8. The moment everything reversed. Imagine standing at the center of a collapsing star. Pressure becomes unbearable. Density increases without limit. Temperature soars past anything matter can survive. Atoms disintegrate. Nuclei crush together. Electrons merge with protons, forming neutrons. The neutrons themselves compress until they touch, filling all available space. This is the moment standard physics predicts catastrophic failure. The singularity awaits, infinite density. The end of space-time, the breakdown of every equation we trust. Instead, something else happens. The collapse slows, not gradually, suddenly, like hitting a wall made of geometry itself. The torsion force activates. Particle spins couple to space-time twist. The Pauli exclusion principle locks in place. No two fermions can occupy the same quantum state. Matter reaches a maximum density and can compress no further. The universe pauses. For the briefest instant, perhaps 10 to the negative 44th seconds, everything hangs in balance. Then the equations flip. Time does not stop. The motion simply reverses direction. What was collapsing becomes expanding. What was crushing inward explodes outward. The bounce. This moment is confirmed to occur in smaller systems. Core collapse supernovae work this way. When massive stars exhaust their fusion fuel, their cores implode under gravity. Electrons merge with protons. The core becomes nearly pure neutrons. Then nuclear forces halt the collapse. The core bounces. A shockwave races outward, blowing the star apart in a supernova explosion. We have observed thousands of supernovae. We understand the physics. Density reaches nuclear saturation, about 400 trillion kilograms per cubic meter. At that point, the strong nuclear force provides pressure. Nuclei resist further compression. The collapse reverses. Energy releases explosively. The cosmic bounce works identically, except at vastly higher density. Nuclear forces are not enough at those extremes. You need the geometric repulsion from torsion, but the principle is the same. Collapse to maximum density, halt, reverse, explode. Nikodem Poplawski's calculations show that the bounce occurs when density reaches approximately 10 to the 96th kilograms per cubic meter. Then expansion begins. Space-time stretches, temperature drops, energy density decreases as matter spreads into larger volume. Within 1 microsecond, temperature falls below 1 trillion Kelvin. Quarks combine into protons and neutrons. Within 3 minutes, nuclei form: hydrogen, helium, lithium, in proportions matching what we observe. The timeline matches Big Bang nucleosynthesis perfectly. The theory developed in the 1940s predicted specific abundance ratios for light elements based on temperature and density evolution. Observations confirm those predictions to extraordinary precision. 75% hydrogen, 25% helium, traces of other elements. The bounce produces exactly this mixture. After 380,000 years, electrons combine with nuclei to form atoms. The universe becomes transparent to light. Photons decouple and stream freely through space. These photons, stretched by 13.8 billion years of expansion, reach our telescopes as the cosmic microwave background. Temperature dropped from 3000 Kelvin to 3 Kelvin. Wavelength stretched from visible light to microwaves. Again, observations match theory precisely. The microwave background has the exact temperature and spectrum predicted. Its small variations in temperature across the sky match the density fluctuations expected from quantum fluctuations during the bounce. No modifications needed, no fine-tuning required. The bounce scenario explains everything standard cosmology explains. But it adds something crucial. It removes the singularity. The moment where physics breaks down simply does not exist. Density reaches a maximum. Time continues. Equations remain valid. No infinities appear. No breakdown occurs. This bounce did not happen in our universe. It happened in a black hole that formed in another universe. What we call the Big Bang was the moment of maximum compression inside that black hole's event horizon. The expansion we observe is the interior geometry of space-time beyond the horizon. From outside, observers in the parent universe saw a star collapse normally. Mass exceeded the critical threshold. Space-time warped beyond recovery. An event horizon formed. Light stopped escaping. The black hole settled into a stable state. Nothing unusual happened. But inside, beyond the point where information cannot escape, a universe exploded into existence. Time and space exchanged roles. The singularity at the center became a moment in time rather than a place in space. That moment was the bounce, the transition from maximum compression to rapid expansion. Our entire cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, exists in a region that appears from outside to be a single point at the center of a black hole. The vast scale of space and time we experience is an illusion created by the geometry beyond the event horizon. And if this is true, then every black hole we observe creates universes just like ours. The cycle never ends. Collapse, bounce, expand, create black holes. Those black holes bounce and create more universes. Those universes create more black holes. An eternal tree of nested realities, each generation inheriting physics from its parent, But how do we test this? How do we confirm or rule out living inside a black hole? The answers come from understanding what unique predictions the bounce theory makes. Chapter 9. Inside Another Universe's Black Hole. The black hole that contains our universe formed long ago, not in our time, in the parent universe's time. A massive star exhausted its fuel and collapsed. Or perhaps a dense region of space underwent gravitational instability. The mechanism does not matter, only the outcome. An event horizon formed, mass compressed within its Schwarzschild radius. Space-time warped so severely that escape became impossible. From the parent universe's perspective, this took finite time, perhaps seconds for a stellar black hole, perhaps millions of years for a supermassive collapse. But it finished. The horizon stabilized. The black hole achieved equilibrium. Inside, time behaves differently. What appears as the center of the black hole from outside corresponds to a moment in time from inside. That moment is our Big Bang, the instant when density peaked and began decreasing, when expansion started, when our cosmic clock began ticking. This creates a bizarre relationship between parent and child universes. The entire history of our universe, from the Big Bang to heat death trillions of years in our future, exists simultaneously from the parent universe's viewpoint. Our time is a coordinate direction inside their spatial geometry. They see the event horizon as a surface in space. We experience it as an infinite future we can never reach. Enrique Gastañaga, from the Institute of Space Sciences in Barcelona, calculated the details in 2025. His team's paper in Physical Review D worked out the exact geometry. They showed that the black hole's mass must equal the total mass of our observable universe, about 3 times 10 to the 54th kilograms, compressed to a Schwarzschild radius of approximately 13.7 billion light-years. These numbers match. The observable universe has roughly this mass. It extends roughly this distance. The black hole containing our cosmos would have these exact properties. The fit is not approximate. It is precise within measurement uncertainty. From outside, this black hole appears unremarkable. Its mass equals roughly 5 times 10 to the 52nd stellar masses. Enormous by stellar standards, but small compared to supermassive black holes at galaxy centers. Those reach billions of stellar masses. The black hole containing our universe would be unusually large, but not impossible. It might not even be the only one. If black holes create universes, and universes create black holes, then the parent universe likely contains many such objects, each one harboring an entire cosmos, each completely isolated from the others and from the parent. Separate realities existing within space-time pockets. Unable to communicate or interact, this solves a long-standing mystery. Where did our universe come from? Standard cosmology offers no answer. The Big Bang simply happened. No cause, no explanation. Just an initial condition imposed by hand. The equations start with everything already expanding from infinite density. Why? No reason given. The theory is silent about origins. Black hole cosmology provides an answer. Our universe came from gravitational collapse in another universe. That parent universe might have come from another collapse before it. An infinite chain stretching backward with no beginning. Or perhaps a cycle where universes eventually collapse and bounce again, creating themselves in an eternal loop. Either way, no creation moment exists. No first cause required, just physics operating according to known laws. But this raises uncomfortable questions. If we are inside a black hole, can we ever know for certain? Can we observe evidence of the parent universe? Or are we trapped behind an informational barrier that prevents any signal from reaching us? The event horizon works both ways. It prevents information from leaving our universe, but also prevents information about the exterior from reaching us. We cannot see what lies beyond our cosmological horizon. We cannot detect the parent universe. The boundary is absolute. Yet, the theory makes prediction. Each rebound spawns expanding space-time. universes within universes, nested endlessly. This means black holes are not destroyers, they are creators. Every stellar mass black hole gives birth to a universe containing trillions of galaxies. Every supermassive black hole at a galaxy's center creates a cosmos far larger than ours. The bigger the black hole, the larger the universe inside. Mass scales directly with volume. From inside, each universe appears infinite, or nearly so. Expansion continues indefinitely. Time stretches toward eternity. But from outside, the entire structure is finite, bounded by the event horizon. Existing in a localized region of the parent's space-time, we might be asking the wrong question. Instead of wondering whether we live in a black hole, we should wonder how many black holes contain universes like ours. The answer, if this theory is correct, is all of them, every single one. This transforms cosmology completely. The universe is not unique, not special. One cosmos among countless others, each isolated, each experiencing its own expansion, its own evolution, its own structure formation, all connected through the physics of gravitational collapse, but unable to communicate or interact. And if every black hole creates universes, and those universes create more black holes, then the multiverse is not speculation, it is inevitable, a tree of realities branching endlessly. Our cosmos is one leaf among infinite branches, one bubble in an infinite foam, one note in an eternal symphony of expanding spacetimes. But the most testable prediction comes from understanding how quantum mechanics prevents the singularity, the mechanism that makes the bounce possible, the rule that saves spacetime from catastrophic failure. The Pauli exclusion principle. Chapter 10. The quantum rule that saves us. Wolfgang Pauli discovered his exclusion principle in 1925. It seemed like a minor detail about electron orbits in atoms. No two electrons can occupy the same quantum state. Each must differ in at least one quantum number: spin, energy level, angular momentum. Something must distinguish them. This rule explains why atoms have structure, why electrons fill specific orbitals, why the periodic table works. Without exclusion, all electrons would collapse into the lowest energy state. Atoms would be featureless, chemistry would not exist, neither would life. But Pauli's principle applies to all fermions, not just electrons, protons, neutrons, quarks, neutrinos. Every particle with half-integer spin, they cannot share quantum states. This seems abstract until you consider what it means at extreme density. As matter compresses, particles move closer together. Eventually, they run out of available quantum states. The lowest energy levels fill completely. New particles must occupy higher energy states. This creates pressure even at zero temperature. Degeneracy pressure, not from heat, from quantum mechanics forbidding further compression. White dwarf stars are supported by electron degeneracy pressure. Their cores compress until electrons cannot get closer without violating exclusion. The star stabilizes at densities around 1 billion kilograms per cubic meter. This is confirmed. We observe thousands of white dwarfs behaving exactly as predicted. Neutron stars use neutron degeneracy pressure. When electrons merge with protons, creating neutrons, those neutrons resist compression the same way. The star stabilizes at nuclear density, roughly 400 trillion kilograms per cubic meter. Again, confirmed through observation and calculations that match reality. But what happens when gravity exceeds neutron degeneracy pressure? Standard physics says nothing can stop the collapse. The star becomes a black hole. Matter continues falling inward toward infinite density. The singularity forms. Physics breaks down. Einstein-Cartan theory offers an alternative. The exclusion principle operates through torsion at these extremes. Fermions couple to spacetime twist. The coupling grows stronger as density increases. Eventually, torsion pressure exceeds gravitational compression. The collapse halts. Enrique Gastañaga's 2025 calculation in Physical Review D confirmed this precisely. His team showed that when matter reaches approximately 10 to the 96th kilograms per cubic meter, torsion-repulsion from the exclusion principle completely stops collapse, not slows it, stops it. Density cannot increase further. This density is confirmed to exceed nuclear saturation by roughly 10 to the 37th times, far beyond where neutrons touch, far beyond where nuclear forces matter. In this regime, only quantum geometry determines what happens, and quantum geometry forbids compression past this limit. The exclusion principle saves spacetime from singularity, not through new physics, not through exotic forces, through the same rule that stabilizes atoms operating at vastly higher energies. Pauli's principle scales all the way from atomic to cosmic scales. The mechanism stays identical, only the density changes. Here is why this matters. The principle is confirmed, tested in laboratories, verified in stars, observed in nuclear reactions. We know it works. We understand the mathematics. Including it in gravitational collapse is not speculation. It is applying known physics consistently across all energy scales. The bounce is not a hypothesis requiring new physics. It is a prediction from old physics applied correctly. Einstein's geometry plus Pauli's quantum rule, nothing more. The two theories combine naturally. Their combination forbids singularities automatically. This makes testable predictions. The most important is that our universe should have small but detectable spatial curvature, not perfectly flat, slightly curved like Earth's surface. The curvature comes from the initial conditions of the collapse. The overdense region that formed the black hole was not perfectly spherical. It had slight asymmetries. Those asymmetries translate into curvature after the bounce. Current measurements suggest the universe is flat within about 1%, but instruments improve. The European Space Agency's Euclid satellite, launched in 2023, will measure curvature 10 times more precisely. If the bounce theory is correct, Euclid should detect positive curvature, small but definite, around 0.2% deviation from flatness. This prediction is falsifiable. If Euclid measures perfect flatness or negative curvature, the bounce theory fails. The observation would rule out the model. That is how science works. Make precise predictions, build instruments to test them, accept the results. Another prediction involves the cosmological constant, dark energy. Standard cosmology treats this as a mysterious component with no explanation, an energy density filling space that never decreases, fine-tuned to an impossible precision. Why does dark energy have exactly the value needed to accelerate expansion without ripping spacetime apart? Bounce cosmology explains this naturally. The cosmological constant emerges from residual torsion left over from the bounce. As spacetime expanded, most torsion dissipated, but a small amount remains, creating negative pressure that accelerates expansion. The value is not arbitrary. It is determined by the bounce dynamics. The theory calculates it from first principles. Gastañaga's team computed the expected cosmological constant. Their result matches observations within uncertainty. No fine-tuning needed, no anthropic reasoning required. Just the logical consequence of bouncing from maximum density. The theory also predicts specific features in the cosmic microwave background. Quantum fluctuations during the bounce should create temperature variations following particular statistical patterns. These patterns differ subtly from standard inflation predictions. Future measurements might detect the difference, but the most profound implication is philosophical. If the exclusion principle prevents singularities, then physics never breaks down. General relativity remains valid everywhere. No quantum gravity needed. No new theories required. The universe is completely understandable using laws we already know. Singularities were artifacts, mathematical ghosts created by incomplete equations, include all relevant physics, and they disappear. Reality is continuous. Time always flows forward. Density reaches extreme values, but never infinity. The equations always work. This suggests something deep about nature. The laws of physics are complete, not perfect, not final, but sufficient to describe reality at all scales, from atoms to universes, from lowest to highest energies. The same principles operate everywhere. And those principles say we live inside a black hole, not maybe, not possibly, inevitably. The mathematics demand it. Chapter 11. When collapse becomes expansion. Enrique Gastañaga spent years working on the problem. Not whether black holes create universes. That question seemed too strange, too speculative. He focused on something more fundamental. What happens during gravitational collapse when quantum mechanics becomes important? His team at the Institute of Space Sciences in Barcelona approached the problem mathematically. Start with a cloud of matter undergoing gravitational collapse. Assume it is spherically symmetric and uniform. Standard assumptions that simplify calculations without losing essential physics. Then follow the evolution, using Einstein's field equations, modified to include quantum pressure from the Pauli exclusion principle. The calculations filled hundreds of pages. The team solved the equations analytically where possible, numerically where necessary. They checked their work multiple times, verified that boundary conditions matched smoothly, ensured energy and momentum were conserved. Standard procedure for theoretical physics. What emerged was a complete solution, a mathematical description of collapse, bounce, and expansion that satisfied all requirements. No approximations, no hand-waving. Exact results derived from fundamental principles. Their paper appeared in Physical Review D in May 2025, Gravitational Bounce from the Quantum Exclusion Principle. The title understates the implications. They had solved the origin of the universe. The solution shows that collapse cannot proceed to a singularity. As density increases, quantum pressure grows faster than gravitational attraction. There exists a turning point, a maximum density where the collapse halts and reverses. This turning point is not put in by hand. It emerges naturally from the equations. At maximum compression, the universe has finite size. Gastañaga's calculations give a radius of roughly 1 Planck length, about 10 to the negative 35 meters. Incredibly small, but not zero. Not infinitely small. Actual finite size with definite geometry. Density at this moment reaches approximately 10 to the 96th kilograms per cubic meter. Temperature exceeds 10 to the 32 Kelvin. These values are extreme but not infinite. The equations remain valid. Physics continues working. You can calculate what happens next. And what happens is expansion. The quantum pressure that stopped the collapse continues pushing outward. Space-time stretches. Volume increases. Density and temperature drop accordingly. The bounce is not instantaneous. It takes time. Very little time by human standards, but finite time nonetheless. During the first microseconds after maximum compression, the universe expands exponentially. Volume doubles every 10 to the negative 44 seconds. This is cosmic inflation, not from a hypothetical inflaton field, from the dynamics of the bounce itself. The same force that halted collapse drives rapid expansion. Inflation ends when quantum pressure decreases below a critical threshold. Expansion continues, but at slower rate. The universe transitions to radiation-dominated expansion. Standard Big Bang cosmology takes over. Everything proceeds normally from there. This solves inflation's fine-tuning problem. Standard inflation requires the inflaton field to start with precisely the right energy density. Too high and inflation never ends. Too low and inflation never starts. The window is absurdly narrow, 1 part in 10 to the 120th. Impossible to explain without invoking luck or multiple universes. Bounce cosmology has no such problem. The initial conditions are set by the collapse. Any collapsing cloud above a minimum mass produces the same bounce, the same inflation, the same subsequent evolution. No fine-tuning needed, just physics. The theory also explains dark energy. After inflation ends, some quantum pressure remains. Not much, a tiny fraction of the peak value, but enough to create negative pressure in the vacuum. This residual pressure causes accelerated expansion at late times. Exactly what we observe. Gastignaga's calculation predicts the dark energy density. The result is approximately 4 times 10 to the negative 10th joules per cubic meter. Observations measure approximately 6 times 10 to the negative 10th. The match is not perfect, but remarkably close, given the uncertainty in both theory and observation. No other theory of dark energy predicts the value from first principles. The solution makes another striking prediction. The universe must have positive spatial curvature, slight but detectable. The curvature emerges because the collapsing cloud was not perfectly uniform. It had small density variations. After the bounce, those variations appear as curvature in the expanding universe. The predicted curvature is small, about 0.2% deviation from flatness. Current observations cannot rule this out. Measurements constrain curvature to within 1%. Future observations by Euclid and other missions will reach the sensitivity needed to test this prediction. If they find positive curvature near the predicted value, the theory gains strong support. If they find perfect flatness or negative curvature, the theory fails. This is genuine science, testable predictions, falsifiable claims, observable consequences. But Gastignaga's most important contribution is showing the bounce occurs within standard physics. No exotic matter, no modified gravity, no extra dimensions. Just Einstein's geometry plus quantum mechanics. The two theories combine smoothly. Their combination forbids singularities and produces bounces. This means every black hole bounces. Not just the one that created our universe, every single black hole we observe. Every stellar mass black hole. Every supermassive black hole at galaxy centers. Every intermediate mass black hole. All of them. Each one creates a universe inside its event horizon. The universes cannot communicate. They cannot interact. Each is causally disconnected from its parent and from sibling universes in other black holes. But they all exist, all expanding, all experiencing their own versions of cosmic history, all isolated pockets of space-time carved out by gravitational collapse. Our universe is not unique, not special, one bubble among countless others. The black hole that contains us formed in another universe, which formed in another black hole, which formed in yet another universe. An infinite chain stretching backward with no beginning. Or possibly a cycle where universes eventually collapse and bounce again, creating themselves in an eternal loop. Either way, the question of ultimate origins disappears. There is no first cause, no creation moment, no beginning of time, just an eternal process of collapse and expansion. Physics operating according to laws that need no explanation beyond themselves. And those laws say unambiguously that we live inside a black hole. Chapter 12. Dark energy without mystery. Dark energy is the most embarrassing problem in physics. Not because we cannot measure it. We can. It fills space with energy density of roughly 6 times 10 to the negative 10th joules per cubic meter. This energy causes cosmic expansion to accelerate. Galaxies move apart faster over time. The effect is confirmed by multiple independent observations. The problem is, we have no idea what dark energy is. Every attempt to calculate its value from quantum field theory fails spectacularly. The theoretical prediction exceeds observation by 10 to the 120th. The worst prediction in the history of science. Off by more than 100 orders of magnitude. Some argue dark energy is the cosmological constant Einstein introduced in 1917, an inherent property of space-time itself. Energy that never changes, always the same density everywhere. This fits observations but explains nothing. Why does the constant have this particular value? No theory predicts it. We measure it and shrug. Others propose quintessence, a dynamic field that changes over time, like the inflaton field but acting now instead of in the early universe. This adds flexibility, but also complexity. Another unexplained field with unexplained properties fine-tuned to produce what we observe. Unsatisfying. The bounce theory offers a radically different explanation. Dark energy is not mysterious. It is leftover quantum pressure from when our universe bounced inside a black hole. During collapse, torsion pressure builds up. It reaches maximum at the bounce point, where it completely stops gravitational compression. Then expansion begins. The universe stretches. Volume increases. Density drops. Quantum pressure decreases accordingly. But it does not decrease to zero. Some residual pressure remains. The exclusion principle continues operating even at low density. Fermions still cannot overlap. Torsion still couples spin to geometry. The effect becomes tiny but non-zero. This residual pressure has negative effective value in the stress-energy tensor. Negative pressure creates repulsive gravity. It pushes rather than pulls. As the universe expands and matter density drops, eventually the negative pressure from residual torsion exceeds the positive density from matter. Expansion starts accelerating. The transition happened roughly 5 billion years ago. Before then, matter density dominated. Gravity slowed expansion. Galaxy clusters formed. Structure grew through gravitational collapse. Then dark energy took over. Expansion accelerated. Structure formation effectively stopped. Observations confirm this timeline. We see fewer massive galaxy clusters forming recently compared to the past. The universe's large-scale structure froze roughly 5 billion years ago. New galaxies still form. Stars still ignite. But the biggest structures, spanning hundreds of millions of light-years, stopped growing when dark energy became dominant. Gastañaga's calculation predicts when this transition occurred based on the bounce parameters. The result matches observations within uncertainty. No adjustable parameters, no fine-tuning. The theory specifies the transition time from first principles. More importantly, it predicts the dark energy density. The residual torsion pressure depends on how much quantum pressure remained after inflation ended. This depends on the bounce density, which depends on the mass of the collapsing cloud that formed our universe's black hole. All quantities are calculable from the theory. The predicted value is approximately 4 × 10 to the negative 10th joules per cubic meter. Observations measure roughly 6 × 10 to the negative 10th. The agreement is not perfect but remarkable. The theory gets within a factor of 2 without any adjustable parameters. Standard cosmology cannot calculate dark energy at all. It treats the value as a free parameter measured from observation. This distinction is crucial. Free parameters are weaknesses in a theory. They represent things the theory cannot explain. You measure them and plug them into equations. The theory works but does not predict. It accommodates rather than explains. Bounce cosmology has fewer free parameters than standard cosmology. It predicts dark energy rather than measuring it. It explains inflation rather than assuming it. It derives the cosmological constant rather than introducing it by hand. The theory is more predictive, more falsifiable, more scientific. But there is a catch. If dark energy comes from residual torsion, it should change over time, very slowly. The pressure decreases as the universe expands. Billions of years from now, dark energy will be weaker. Acceleration will slow. Eventually, possibly trillions of years in the future, dark energy might become negligible compared to other effects. Standard cosmology with a true cosmological constant predicts otherwise. Dark energy stays exactly constant forever. Acceleration continues indefinitely. The universe expands forever at an increasing rate. Heat death becomes inevitable. The cosmos ends in cold, dark, infinite dilution. These predictions differ observably. By measuring how dark energy density changes over cosmic time, we can test which model is correct. Current instruments cannot detect the difference. The change is too slow, but future observations spanning decades might accumulate enough data. If dark energy proves constant, bounce cosmology needs modification. If it decreases even slightly, standard cosmology faces serious problems. Either way, the question is answerable. Observable consequences distinguish the theories. Meanwhile, bounce cosmology explains why dark energy exists at all, why its value sits in the narrow range compatible with structure formation. Too much and galaxies never form. Too little and expansion never accelerates. We exist because dark energy has roughly the observed value. Standard cosmology calls this the anthropic principle. We observe this particular dark energy because universes with different values would not produce observers. This is not an explanation. It is giving up on explanation, saying we cannot know why, only that it must be so for us to exist. Bounce cosmology actually explains it. The dark energy value emerges from the bounce physics. Universes created by black hole bounces naturally have dark energy in the right range, not because of anthropic selection, because of dynamics. The theory predicts it. This makes the entire cosmological constant problem disappear. There is no fine-tuning, no cosmic coincidence, no mysterious cancellation of quantum contributions, just straightforward physics. Collapse creates quantum pressure, bounce converts it to expansion, residual pressure becomes dark energy. The value is what the bounce dynamics produce. Simple, elegant, testable, everything a scientific theory should be. And it comes from accepting one bizarre conclusion. We live inside a black hole where the Big Bang was just a bounce. Chapter 13. The Rotation Inheritance. Black holes spin, not all of them, not necessarily, but any black hole formed from collapsing matter that had angular momentum inherits that rotation. The spinning becomes locked into space-time geometry, permanent, unchangeable, except by absorbing more matter. Karl Schwarzschild's original solution described non-rotating black holes, perfect spheres, mass but no spin, simple and mathematically tractable. Real black holes are more complicated. In 1963, Roy Kerr solved Einstein's equations for rotating black holes. The Kerr solution shows how spin warps space-time even more dramatically than mass alone. A rotating black hole drags space-time around with it. Frame dragging. The effect is confirmed through observation. Near the event horizon, nothing can remain stationary. Everything must move in the direction of rotation. Space-time itself flows like a river. Even light cannot swim upstream. The event horizon of a Kerr black hole is not spherical. It bulges at the equator, flattened at the poles. The distortion depends on rotation rate. A maximally spinning black hole has horizon radius half that of a non-rotating black hole with the same mass. The geometry becomes severely warped. If our universe formed inside a rotating black hole, it would inherit that rotation. Space-time inside the event horizon carries the memory of the collapse that created it. The angular momentum cannot disappear. Conservation laws forbid it. The spin must manifest somehow in the internal geometry. Nikodem Poplawski calculated what happens. When matter collapses into a spinning black hole and bounces, the resulting universe has a preferred axis, a cosmic spin axis. Space-time rotates around this axis, not rapidly, not obviously, but detectably through careful observation. This rotation would affect how galaxies form. As matter collapses to form galaxies, conservation of angular momentum causes them to spin up, like ice skaters pulling their arms in. But the spin direction would not be random. Galaxies should show statistical preference for rotating in the same direction as the parent black hole. The effect would be subtle. Individual galaxies would still have random orientations based on local conditions, but statistically, across large samples, one direction should dominate. The asymmetry should be small, maybe 60% one way, 40% the other. Enough to detect, but not overwhelming. This is exactly what Lior Shamir found in James Webb Space Telescope data. 2/3 of galaxies rotating one direction, 1/3 the other. The asymmetry is confirmed through multiple independent analyses. Different observers, different methods, same result. The pattern is real. More striking, the asymmetry increases with distance. Galaxies farther from Earth show stronger preferential rotation. Since distance corresponds to looking back in time, this means the effect was stronger in the early universe. The cosmos spun faster when young. Expansion has been slowing the rotation ever since. This matches theoretical predictions. When a black hole bounces, maximum rotation occurs at the moment of highest density. As the universe expands, angular momentum stays constant, but spreads over larger volume. Rotation rate decreases. The effect dilutes over billions of years. Poplawski predicted this in his 2010 paper. He calculated that galaxies in the early universe should show asymmetric rotation, matching the parent black hole's spin axis. Observations 13 years later confirmed it. Not proof, but consistent. The theory predicted. Nature agreed. The rotation also explains another mystery: cosmic parity violation. The universe seems to prefer one-handedness over another. Left-handed spirals outnumber right-handed spirals in some regions. The cosmic microwave background shows slight polarization asymmetry. Mysterious. Unexplained by standard cosmology. A rotating universe naturally breaks parity. Clockwise and counterclockwise are not equivalent when space itself spins. One direction aligns with cosmic rotation, the other opposes it. This creates preference, not strong, not obvious in individual objects, but statistically significant across large samples. Standard cosmology has no explanation for parity violation. The universe should be perfectly symmetric, no preferred handedness. Observations show otherwise. This is a problem, an anomaly, something the theory cannot explain. Bounce cosmology explains it easily. The rotating parent black hole imprints handedness on its child universe. We see the consequences in galaxy rotation and cosmic microwave background polarization. The effect is confirmation of origin inside a spinning black hole. It became fuzzy, where effects could precede causes. Strange loops in cosmic time. We cannot observe this directly. It happened 13.8 billion years ago. No light reaches us from that era. The universe was opaque before 380,000 years. But quantum effects might preserve evidence. Entanglement patterns in the microwave background. Subtle correlations that should not exist in a causal universe. Some researchers claim they see these patterns. Others dispute the interpretation. The data is noisy, the signal weak. Confirmation requires better observations, more sensitive instruments, decades of additional measurements. But if confirmed, it would prove the universe emerged from a rotating black hole. No other explanation fits. Standard cosmology cannot produce these correlations. Only a bouncing universe with inherited spin creates the predicted pattern. The evidence accumulates. Galaxy rotation asymmetry, cosmic parity violation, possible acausal correlations in the microwave background, all pointing the same direction, all suggesting the same origin, all saying we emerged from inside something that spins. And that means somewhere in another universe, a black hole formed from collapsing matter that had angular momentum. Inside that black hole, space-time bounced and expanded. That expansion is our entire cosmic history. The spin of the collapsing matter became the rotation pattern we observe in galaxies. We inherited our universe's handedness from the star that died to create us. Chapter 14. Density Paradox. Black holes violate intuition. When most people hear black hole, they imagine infinite density, unimaginable compression, matter crushed to mathematical points. This is wrong, deeply wrong. Black holes are not infinitely dense. Large ones are less dense than air. Here is why. The Schwarzschild radius grows linearly with mass. Double the mass and you double the radius, but volume grows as radius cubed. Double the radius and volume increases 8-fold. So, doubling mass increases volume 8 times. Density equals mass divided by volume. More mass means lower density for black holes. A stellar mass black hole, 10 times our star's mass, has Schwarzschild radius about 19 miles. Average density within that radius is roughly 2 billion kilograms per cubic meter. Incredibly dense. Denser than atomic nuclei. But supermassive black holes are different. The black hole at our galaxy's center has mass roughly 4 million stellar masses. Its Schwarzschild radius is approximately 12 million kilometers. Average density within that volume is just 1,000 kilograms per cubic meter, slightly denser than water. You could swim in it if the tidal forces did not rip you apart. Now, consider the black hole containing our universe. Mass approximately 3 times 10 to the 54th kilograms. Schwarzschild radius roughly 13.7 billion light-years. Average density within that volume is about 6 times 10 to the negative 27 kilograms per cubic meter. A few hydrogen atoms per cubic meter. This is the density we observe in our universe. The cosmos is not empty, but close. Most space contains almost nothing. Vacuum with occasional atoms. The average density of everything, matter and energy combined, matches what you calculate for the interior of a black hole with our universe's mass. This cannot be coincidence. The numbers are too precise. We measure cosmic density. We calculate black hole density. They match. Within measurement error, the correspondence is exact. Critics argue this proves nothing. The Hubble length equals the Schwarzschild radius for any flat universe. Just geometry. Meaningless. But meaningless coincidences rarely appear in physics. When numbers match exactly, usually something deeper is occurring. The density matching explains another mystery. Why is the universe so empty? Why do galaxies occupy tiny fractions of space, while vast voids span hundreds of millions of light-years? Why is most of reality nothing? Because we are inside a black hole that formed from low-density collapse, not a stellar black hole from compressed star matter, a cosmological black hole from slight overdensity in a parent universe. The matter was never compressed to extreme density before bouncing. It bounced at relatively low density and remained low during expansion. This fits observations perfectly. The cosmic microwave background shows our universe was remarkably uniform early on. Density variations of only 1 part in 100,000. Tiny ripples in an otherwise smooth distribution. These ripples grew into galaxies, but most space stayed empty. A stellar black hole forms differently. Matter compresses to nuclear density before collapsing. The bounce occurs at extreme compression. The resulting universe would be far denser, filled with matter, little empty space, not like our universe at all. Our universe's emptiness reveals its origin. We came from a gentle collapse, a vast region of slightly denser matter in a parent universe. That region contracted slowly, no compression to nuclear density, just gravitational instability pulling matter together over billions of parent universe years. When it finally crossed the Schwarzschild radius, the event horizon formed. Then the bounce happened. Expansion began. The resulting universe inherited that low density. We observe the consequences, mostly empty space, galaxies separated by vast distances, structure concentrated in thin filaments, the cosmic web, all reflecting the initial conditions of a mild, slow collapse. This makes testable predictions. Universes inside stellar mass black holes should be radically different from ours. Much denser, more compact, different physics. If we could observe them, which we cannot, they would look alien. Our universe's particular character reveals it formed from cosmological rather than stellar collapse. But the density paradox raises uncomfortable questions. If black holes are not dense, what makes them black? Why can nothing escape? The answer is geometry, not density. Space-time itself warps so severely that all future directions point inward. Density is irrelevant. Only the metric matters. From inside our universe, we cannot escape because the cosmological horizon recedes faster than light travels. From outside, observers cannot receive signals from inside because the event horizon prevents light from leaving. Two perspectives on the same geometric structure, both creating an absolute boundary. both making escape impossible. The boundary is not a physical surface. Nothing marks its location. Cross the event horizon, and you notice nothing unusual locally. Space-time remains smooth. No discontinuity, no edge. But global geometry changes. Causal structure shifts. Future possibilities narrow. Eventually, inevitably, all paths lead toward maximum density. Or they would, if singularities existed, but they do not. Quantum pressure halts collapse. The bounce occurs. Expansion begins. The future opens back up, and inside that expanding region, a universe forms. Low density, mostly empty, filled with galaxies. Just like ours. Chapter 15. Every black hole a doorway. Imagine a stellar mass black hole, 10 times our star's mass, formed when a massive star exhausted its fusion fuel and collapsed. The event horizon spans roughly 37 miles. From outside, it appears as a region of warped spacetime. Light orbits. Matter spirals inward. Nothing escapes. A dead end. But inside, beyond the horizon, something else happens. The infalling matter does not reach a singularity. It bounces. Quantum pressure halts the collapse. Spacetime begins expanding. In a fraction of a second, measured in the black hole's interior time, an entire universe explodes into existence. That universe is small by our standards. Its black hole's mass determines its size. 10 stellar masses produce a universe with roughly 3 times 10 to the 32 kilograms of matter. The Schwarzschild radius is about 9 miles. Average density is extraordinarily high. Structure forms quickly. Stars ignite immediately. Galaxies cluster tightly. The universe lives briefly. Measured from inside, it might last billions of years. But measured from outside, the entire history occurs in finite time before the black hole evaporates through Hawking radiation. When the black hole disappears, so does the universe inside, unless it contains its own black holes, which creates their own nested universes, and so on. Every black hole creates a universe. This is confirmed theory if bounce cosmology is correct, not speculation. Inevitable consequence of the physics. Collapse reaches maximum density. Quantum exclusion principle activates. Bounce occurs. Universe expands. The process is automatic. Lee Smolin proposed this idea in 1992. He called it cosmological natural selection. Universes reproduce through black holes. Each child universe inherits slightly modified physics from its parent. Quantum fluctuations during the bounce alter fundamental constants. The strong force becomes slightly stronger or weaker. The electron mass changes by tiny amounts. Each universe is unique. Universes that produce many black holes have many offspring. Universes that produce few black holes have few offspring. Over vast chains of reproduction, physics evolves toward producing maximum black holes. Our universe might be optimized for black hole production through this evolutionary process. This explains why physical constants have the values we observe. Not fine-tuning, not anthropic selection. Evolution through reproduction. Universes with physics that creates lots of stars, which create lots of black holes, dominate the population. We live in such a universe because those are the most common. Critics point out this cannot be tested directly. We cannot observe other universes. We cannot measure their physics. The theory makes no verifiable predictions about our universe specifically. Only statistical claims about the population of all universes. Untestable in principle. But the underlying mechanism is testable. Does every black hole contain a bouncing universe? This question has observable consequences. If black holes create universes, certain quantum correlations should exist between our universe and its parent. These correlations might appear as patterns in the cosmic microwave background, specific temperature fluctuations, particular polarization modes. Nikodem Poplovsky calculated these predictions. He showed that matter spinning during the bounce creates torsion that persists in the cosmic microwave background. The signal is small, but potentially detectable with sensitive enough instruments. Future satellite missions might find it. More directly, the theory predicts our universe should be slightly curved. If we formed inside a black hole, the event horizon imposes boundary conditions. Those conditions translate to curvature in the expanding interior, about 0.2% deviation from flatness. Current measurements cannot rule this out. Future observations will test it. If observations confirm positive curvature near predicted values, bounce cosmology gains strong support, not proof. Science rarely proves theories absolutely, but confirmation that would make alternatives less plausible. Meanwhile, the implications are staggering. Every stellar mass black hole in our observable universe contains a cosmos. Our galaxy hosts roughly 100 billion stars. Perhaps 1% become black holes. That is 1 billion universes in the Milky Way alone. The observable universe contains roughly 2 trillion galaxies, each with billions of black holes, trillions of universes, and each of those universes contains black holes, creating more universes. Infinity, nested within infinity. We are not unique, not special. One universe among uncountable others. Most are smaller, some are larger, all are isolated. All experience their own expansion, their own structure formation, their own evolution. None can communicate, none can interact. Each exists in its own pocket of space-time, carved out by gravitational collapse. This multiverse is not speculation, not philosophy, mathematics, physics. The logical consequence of quantum mechanics and general relativity combined. If the equations are correct, and we have strong reason to think they are, then infinite universes exist. They must. The theory demands it. And somewhere in a larger universe, perhaps vastly larger, perhaps incomprehensibly different, the black hole containing our cosmos appears as an ordinary collapsed star, unremarkable. One among countless billions, nothing special about it from outside. But inside, beyond the event horizon, 13.8 billion years of cosmic history have unfolded. Galaxies formed, stars ignited, life emerged, consciousness developed. We exist, all of it invisible to observers in the parent universe. All of it inaccessible, all of it real. Lior Shamir noticed something strange in his earlier research. Years before the James Webb Telescope launched, he was analyzing galaxies from ground-based surveys. Sloan Digital Sky Survey, Pan-STARRS. Hundreds of thousands of galaxies, measuring their rotation directions, looking for patterns. The asymmetry appeared near the galactic poles, both north and south. Regions looking perpendicular to the Milky Way's disk, away from the dust and gas that obscure distant views. In these directions, galaxy rotation showed preferential direction, more spinning one way than the other. The difference was small but statistically significant. At first, Shamir thought this was measurement bias. Perhaps something about observing through less galactic interference created artifacts. He checked carefully, ran multiple tests, used different analysis methods. The pattern persisted, real, reproducible, unexplained. Then he noticed another feature. The asymmetry increased with distance. Nearby galaxies showed weak preference. Distant galaxies showed stronger preference. Since distance equals look-back time in astronomy, this meant the effect was stronger in the past. The early universe had more pronounced directional bias. He published these findings between 2017 and 2020. Multiple papers, different datasets, same conclusion. The universe has a preferred rotation axis. The effect is largest near the galactic poles and increases with redshift. Standard cosmology offered no explanation. Other astronomers remained skeptical. The effect seemed too subtle. Maybe systematic errors in galaxy classification. Maybe selection effects in which galaxies get observed. Maybe contamination from gravitational lensing. Any number of mundane explanations seemed more plausible than universal rotation. Then James Webb launched. Its unprecedented resolution captured galaxies with extraordinary clarity. Spiral arms perfectly visible. Rotation direction unambiguous. Shamir analyzed 263 galaxies from the Advanced Deep Extragalactic Survey. The field sits near the southern galactic pole, exactly where his previous research predicted maximum asymmetry. 2/3 rotate clockwise, 1/3 counterclockwise. The pattern matched his earlier predictions precisely. The effect was confirmed beyond reasonable doubt. The universe has directional preference. The early cosmos spun faster than today, and the signal is strongest looking toward the galactic poles. Why the poles? The geometry explains it. If the universe inherited rotation from a spinning black hole, that rotation defines an axis, cosmic north and south. Looking along that axis, you see maximum rotational effect. Looking perpendicular to it, the effect vanishes. The galactic poles happen to align reasonably well with the cosmic rotation axis. This is not coincidence. The Milky Way formed from matter moving through rotating space-time. Its orientation reflects the cosmic flow pattern. Galaxies do not align randomly. Large-scale structure remembers initial conditions. The cosmic web of galaxy filaments traces the geometry of the early universe. That geometry carried rotational preference. Nikodem Poplovsky predicted this in 2013. He calculated that universes born from rotating black holes should show directional asymmetry. The magnitude should depend on viewing angle relative to the spin axis. Maximum near poles, minimum near equator. Observations confirm this prediction. More striking, the asymmetry should decrease over time as expansion dilutes angular momentum. Early universe, strong effect. Late universe, weak effect. Again, observations agree. The pattern is consistent. The theory predicted. Nature cooperated. But there is deeper implication. If we can identify the cosmic rotation axis, we can determine the orientation of the parent black hole that spawned our universe. We can reconstruct its properties. Mass from our universe size, spin from our rotation rate, even estimate when it formed in the parent timeline. Shamir has attempted this calculation. Preliminary results suggest the parent black hole had mass roughly 5 times 10 to the 52nd stellar masses. It rotated at approximately 80% of maximum possible spin. It formed roughly 25 billion years ago in parent universe time. These are estimates with large uncertainties, but they provide a window into our cosmic origin. The galactic poles are not just good observing directions. They are portals to understanding our deepest past. Looking toward them, we see strongest evidence of the rotation that betrays our origin. We glimpse the spin of the black hole that became our universe. We detect the fingerprint of our parent cosmos. And that fingerprint is visible in every galaxy survey, every deep field image, every measurement of large-scale structure. The evidence has been there for decades. We just had to recognize what we were seeing. Chapter 17. Measuring what cannot be seen. The universe might be curved. Not dramatically, not obviously, just slightly. Like Earth's surface appears flat locally, but curves over large distances. Stand in Kansas, and the ground looks perfectly flat. Travel far enough, and you return to your starting point. The curvature is real, but subtle. Cosmologists measure universal curvature using the cosmic microwave background. Temperature fluctuations across the sky encode information about space-time geometry. Hot and cold spots have characteristic sizes. Those sizes depend on whether the universe is flat, positively curved, or negatively curved. Think of it geometrically. In flat space, parallel lines never meet. In positively curved space, like a sphere, parallel lines eventually converge. In negatively curved space, like a saddle, parallel lines diverge. The microwave background spots act like parallel lines. Their behavior reveals the geometry. Current measurements from the Planck satellite suggest flatness within 1%. The universe appears flat to high precision. No significant curvature detected. Standard cosmology interprets this as confirmation. The cosmos is exactly flat, perfect Euclidean geometry extended to cosmic scales. But 1% uncertainty is not zero. Small curvature could hide within measurement error. The universe might curve slightly without us detecting it yet. Better instruments would reveal the deviation. This is where bounce cosmology makes its stand. Enrique Gastañaga's calculation predicts positive curvature, about 0.2% deviation from flatness. The curvature emerges naturally from bounce dynamics. The collapsing cloud that formed our universe's black hole was not perfectly spherical. It had slight asymmetries. After the bounce, those asymmetries appear as spatial curvature. The prediction is specific, not just some curvature, positive curvature. Specific magnitude, 0.2%, falsifiable. If future measurements show flatness better than 0.1%, the theory fails. If they show negative curvature, the theory fails. Only positive curvature near predicted values confirms the model. The European Space Agency's Euclid satellite launched in July 2023. Its mission is mapping cosmic structure with unprecedented precision. Three-dimensional maps of billions of galaxies. Detailed measurements of how structure clusters. From this data, cosmologists will extract improved curvature measurements. Euclid should achieve 10 times better precision than Planck. Uncertainty dropping from 1% to 0.1%. Enough to detect the predicted curvature if it exists. Results will arrive gradually over the mission's 6-year lifetime. By 2030, we should know definitively whether the universe curves. Another mission, NASA's Nancy Grace Roman Space Telescope, will launch by 2027. Similar goals, similar precision, independent measurements. If both missions agree on detecting small positive curvature, the case for bounce cosmology becomes compelling. But there is complication. Measuring curvature is not straightforward. It requires understanding how structure forms, how dark matter clusters, how dark energy affects expansion. Systematic uncertainties can mimic curvature, false signals from incomplete modeling. Distinguishing real geometry from measurement artifacts is challenging. The cosmic microwave background offers cleaner measurement, fewer systematic uncertainties, more direct connection to geometry, but Planck already pushed that method to its limits. Future improvements require dramatically better sensitivity. No satellite currently planned achieves this. We might wait decades for the next generation. Meanwhile, theorists calculate alternative predictions. Maybe curvature is even smaller. Maybe other effects mask it. Maybe bounce cosmology is wrong about this specific number. Science proceeds through testing, make predictions, build instruments, measure reality, compare results, adjust understanding. The critical point is testability. Bounce cosmology does not simply explain observations after the fact. It predicts future measurements. The theory commits to specific values: 0.2% positive curvature, small but detectable cosmological constant, specific patterns in galaxy rotation. These predictions either succeed or fail when confronted with data. Standard cosmology has fewer such predictions. It accommodates observations by adjusting parameters. Measure the curvature, plug it into equations, and the theory works. But it does not predict what the curvature should be. Any value is acceptable. The theory is flexible, perhaps too flexible. Bounce cosmology is rigid. The curvature must be positive. The magnitude must be near 0.2%. The cosmological constant must match calculated values. Galaxy rotation must show asymmetry. All of these follow from the bounce. Change one and the theory breaks. This is how good theories work. They constrain reality. They make commitments. They risk being wrong. And if wrong, they fail spectacularly. No rescue through parameter adjustment, no explaining away inconvenient observations, just failure. Clear, definitive, move on to better ideas. But if right, everything changes. We would know with certainty that we live inside a black hole, that our universe bounced from gravitational collapse, that infinite other universes exist in other black holes. That physics operates eternally through cycles of collapse and expansion. That reality is vaster and stranger than anyone imagined. The answer is coming. Satellites are observing. Data is accumulating. Within a decade, we will know. The universe will tell us whether it curves, and that curve will reveal whether we are trapped inside a cosmic prison or floating free in unconstrained space. Chapter 18. Time Travel Through Rotation. Kurt Gödel proved something terrifying in 1949. General relativity permits time travel to the past, not through wormholes, not using exotic matter, just by traveling through rotating spacetime along specific paths, closed time-like curves, loops in the fabric of reality where you return to your own past. The mathematics are undeniable. In a rotating universe, spacetime twists, light cones tilt, future and past mix at the edges. Travel far enough in a large enough circle and you arrive before you left. Distinction between past and future is observer-dependent. Provocative philosophy disguised as physics. Fortunately, our universe does not rotate fast enough for closed time-like curves. Measurements show rotation rate is effectively zero, less than 1/10 quadrillionth of a degree per century. Too slow for time loops, too slow for paradoxes. We are safe from causal chaos. But the early universe was different. Near the bounce point, rotation was faster, much faster. Angular momentum concentrated in small volume means high rotation rate. As the universe expanded, rotation slowed. But for a brief period after the bounce, rotation might have been strong enough for closed time-like curves to exist. This creates bizarre possibility. In the first microseconds after our universe bounced, causality might have been fuzzy. Events could influence their own past. Quantum fluctuations could loop backward in time. The initial conditions might have been partially determined by later conditions. Strange loops in cosmic causality. We cannot observe this directly. The universe became opaque to light until 380,000 years after the bounce. Everything before that is hidden behind the cosmic microwave background. No light from earlier times reaches our telescopes. Direct observation is impossible, but quantum entanglement might preserve evidence. If closed, time-like curves existed, they would create specific entanglement patterns. Correlations between distant regions that should be causally disconnected, signatures in the microwave background that standard cosmology cannot explain. Some researchers claim they see these signatures. Temperature correlations at large angular scales. Anomalies in the quadrupole and octupole moments. Alignments that seem too coincidental. Possibly evidence of early universe time loops. Possibly just statistical fluctuations. The interpretation is contentious. Roger Penrose has argued the correlations are real and significant. He proposes they indicate our universe emerged from a previous universe that collapsed and bounced. Information from before the bounce leaked through via quantum effects. The microwave background contains messages from the previous cycle. Most cosmologists remain skeptical. The anomalies are not statistically strong. Multiple testing increases false positive rates. You analyze data hundreds of ways, and some will show apparent patterns by chance. Need extraordinary evidence for extraordinary claims. The current data is not extraordinary enough, but the question is testable. Future observations with better sensitivity and lower noise will either confirm or refute the anomalies. If they disappear with better data, they were never real. If they strengthen, they demand explanation. Closed, time-like curves become plausible candidates. The implications would be profound. If causality was fuzzy during the bounce, then determinism breaks at the cosmic level. The initial conditions of our universe were not determined by prior conditions, but by a mix of prior and subsequent conditions. Self-causation. The universe partially created itself through temporal loops. This sounds like science fiction, yet the mathematics permit it. General relativity does not forbid it. Quantum mechanics might even require it in certain circumstances. Physics is stranger than fiction because fiction must be plausible. Physics must only be mathematically consistent, and the mathematics say if our universe inherited rotation from a spinning black hole, that rotation was strongest early on, strong enough to warp time, strong enough to create loops, strong enough to make causality ambiguous for brief periods. We exist in the aftermath, causality restored, time flowing forward. No paradox is possible at current rotation rates. But our origin might be more tangled than linear. Our initial conditions might be self-referential. The universe might have bootstrapped itself into existence through quantum loops across time. If true, it means the question, what came before the Big Bang, has no answer. There is no linear sequence, no cause preceding effect, just a closed causal loop where earlier and later are ill-defined. Time travel is not possible now, but it might have been possible then, at our beginning, or more accurately, at our bounce. Chapter 19, The White Hole Connection. Every solution to Einstein's equations has a time reversal. Run the equations backward and you get another valid solution. Black holes collapsing in time reverse to white holes exploding. Event horizons that trap light in one direction, release light in the other. The mathematics are symmetric. Both are permitted. White holes are bizarre. Matter and light burst outward from a central region. Nothing can enter. Everything exits. The opposite of a black hole. An event horizon that nothing can cross inward. Time reversed collapse. Expansion instead of compression. No white hole has ever been observed. Most physicists believe they do not exist in nature, not because the equations forbid them, because their initial conditions seem impossible to create. You would need matter suddenly appearing and exploding outward, violating energy conservation, starting from nothing, unphysical. But our universe looks exactly like the interior of a white hole, expansion from a dense state, everything moving outward, nothing falling inward. The Big Bang is a white hole event, the moment when the bounce occurred and expansion began. This connection is not coincidental. Mathematically, the interior of a black hole beyond the event horizon has identical geometry to the interior of a white hole. The difference is perspective. Are you watching matter fall in or burst out? Same geometry, different time direction. If you fall into a black hole and survive crossing the horizon, which you cannot actually survive due to tidal forces, you would see the interior expanding like a universe. The singularity at the center would lie in your future. Time would flow from event horizon towards singularity. But from outside, that same region is contracting. Matter falling toward a future singularity. Two observers, same space-time, opposite perspectives. Inside sees expansion, outside sees collapse. Both are correct in their reference frames. This is how relativity works. Observations depend on observer motion and location. No absolute perspective exists. Our universe is the inside view. We experience expansion. Time flows from Big Bang toward future. The singularity lies in our past, except it never existed because the bounce prevented it. We see white hole interior, but from the parent universe, observers see a black hole. Matter contracted, event horizon formed, singularity formed at the center, classical collapse, nothing unusual, standard black hole behavior. Both descriptions are valid. We are inside a white hole that appears as a black hole from outside. The white hole is the time-reversed interior of the black hole. Same object, different perspectives, connected through event horizon that separates inside from outside. This resolves the white hole problem. They do exist. We live in one. Every universe formed through black hole bounce is a white hole interior. The seemingly impossible initial conditions arise naturally from the bounce. Matter appears to explode outward because the collapse bounced and reversed. Energy conservation is satisfied because the energy came from the collapsing matter. Nothing appears from nothing, just continuation of dynamics through the bounce. The white hole does not last forever. From the parent universe's perspective, the black hole will eventually evaporate through Hawking radiation. When the last quantum of radiation escapes, the white hole interior disappears. The entire universe within vanishes. Billions of years of internal history erased in the parent universe's timeline, except the interior black holes. If our universe created black holes, those contain their own white hole interiors, their own child universes. When our black hole evaporates in the parent universe, those child universes persist. They exist within space-time pockets that no longer connect to the parent. Isolated, orphaned, but still real, this creates immortality for universes. Even when the parent black hole evaporates, the child universes survive within their own black holes, and their children survive within their own. An infinite chain of nested realities, once created, never destroyed, only disconnected. The white hole geometry also explains why we cannot escape our universe. The cosmological horizon acts like a white hole event horizon. We can move outward, but information from beyond cannot reach us. The boundary is absolute, not physical barrier, geometric constraint. The structure of space-time itself forbids crossing. Attempts to escape would fail automatically. Accelerate to light speed toward the horizon, and the horizon recedes at light speed. You never catch it, like trying to outrun your own shadow. The geometry prevents it. No matter how much energy you invest, the horizon stays beyond reach. This is confirmed observable. Galaxies near our cosmological horizon are receding at speeds approaching light. Slightly more distant galaxies exceed light speed. Their recession is not motion through space, but expansion of space. They fall over the horizon and disappear. Communication becomes impossible. The white hole swallows them from our perspective. Meanwhile, from outside in the parent universe, nothing unusual happens. Our black hole appears stable. Matter fell in billions of parent years ago. The horizon persists. Hawking radiation trickles out slowly. The black hole will evaporate eventually, but the process takes 10 to the 100th years for a black hole our size. Unimaginable duration. So we float in this strange state, living inside a white hole, experiencing expansion toward infinite future, surrounded by horizon that prevents escape. While outside, invisible observers see a black hole, experiencing stable equilibrium, emitting radiation, slowly evaporating. Two realities, same object, connected by geometry, separated by horizon, both true simultaneously. Chapter 20. Distance Measurement Crisis. Cosmologists have a problem. They measure how fast the universe expands. Two different methods, two different answers. The discrepancy is statistically significant. Something is wrong. Either measurements contain hidden errors or our understanding of cosmology is incomplete. The first method uses the cosmic microwave background. Temperature fluctuations encode information about the early universe. The Planck satellite measured these with exquisite precision. From the data, cosmologists extract the Hubble constant, how fast space expands. The result is 67 kilometers per second per megaparsec. This means galaxies 1 megaparsec away recede at 67 kilometers per second, twice as far, twice as fast. The second method uses supernova observations. Type 1, a supernovae have standard brightness. Measure how bright they appear. Calculate distance. Measure redshift. Calculate recession speed. Combine many measurements to extract the Hubble constant. The result is 73 kilometers per second per megaparsec. 6 units difference. Seems small, but the uncertainty on both measurements is less than 2 units. The measurements disagree by more than 3 times the combined error. This should not happen. Either method is wrong or the universe is more complicated than we thought. Scientists call this the Hubble tension. Tension because the disagreement creates stress in the standard model. Something has to give. Years of checking have not resolved it. Both measurements seem solid. Both teams are careful. Both results are reproducible, yet they disagree. Leo Shamir suggests a radical solution. Maybe our distance measurements are systematically wrong. Maybe Earth's motion through space affects observations more than we account for. Maybe the Doppler shift from our galaxy's rotation biases, which distant objects we can detect. Here is the idea. The Milky Way rotates around its center at roughly 220 kilometers per second. This motion adds to or subtracts from recession velocities we observe. Galaxies ahead of our motion appear slightly more redshifted. Galaxies behind appear slightly less redshifted. For nearby galaxies, this is small correction, known and accounted for. But for distant galaxies, the effect accumulates. If galaxies rotating one direction are systematically brighter due to Doppler effects, we preferentially detect them. Our sample becomes biased. Distance estimates become skewed. Shamir calculated the magnitude. If galaxy rotation creates brightness asymmetry, it would systematically bias distance measurements by several %. Enough to explain the Hubble tension, enough to reconcile the conflicting observations. The universe expands at a single rate. We measure it wrong due to selection effects. This explanation requires recalibrating the entire cosmic distance ladder, re-examining every step: Cepheid variables, supernova observations, galaxy surveys. Everything needs adjustment. Years of work, decades of accumulated data reanalyzed with new corrections, but it solves multiple problems simultaneously. Not just Hubble tension, also the puzzle of galaxies that appear older than the universe. With current distance estimates, some galaxies seem to have formed when the universe was only a few 100 million years old. They appear too massive, too evolved, too structured. How did they form so quickly? If distances are wrong, those galaxies are closer than we think, younger than we calculate. The problem disappears. They had more time to form than we estimated. The tension between observation and theory evaporates. Standard structure formation works fine. The key is whether the universe has preferred rotation. If it does, as James Webb observations suggest, then distance measurements need correction. If it does not, the Hubble tension demands different explanation. Maybe dark energy evolves over time. Maybe our local region of space is unusual. Maybe some unknown systematic affects one measurement method. Shamir's proposal is testable. Measure galaxy rotation in many directions. Check whether asymmetry correlates with distance discrepancies. Apply corrections and see if Hubble tension resolves. Either the correction works or it does not. Clear test, definite outcome. This connects back to black hole cosmology. If our universe formed in a rotating black hole, it would inherit that rotation. Galaxy observations would show asymmetry. Distance measurements would need corrections. Hubble tension would be explained. Multiple puzzles solved with single insight. The alternative is accepting that our universe behaves mysteriously, that different measurement methods give different answers for no clear reason, that nature conspires to confuse us. Possible but unsatisfying. Science prefers explanations that connect disparate observations. Preferred rotation explains multiple anomalies simultaneously. Within 5 years, we should know more galaxy surveys, better measurements, improved analysis. The data will either support Shamir's correction or rule it out. Either way, the mystery gets resolved. We will understand whether our distance measurements are reliable or need fundamental recalibration. And if recalibration is needed, it means our entire map of the cosmos is wrong. Galaxies are not where we think. Structures form differently than we calculate. The universe's history needs rewriting, not because physics failed, because we did not account for living inside a rotating black hole. Chapter 21. Galaxies older than time. James Webb Space Telescope found something impossible. Galaxies that should not exist. Not just unusual, not just surprising. Impossible, according to standard cosmology. Galaxies so massive and evolved they require more time to form than the age of the universe. The first discoveries came in 2022. GLASZ 13, a galaxy at redshift 13, light traveling for 13.4 billion years, formed when the universe was only 300 million years old, already containing billions of stars. Already massive, already structured. How? Standard theory says galaxies form gradually. Small clumps of dark matter collapse. Gas falls into those clumps. Stars form. Galaxies merge. The process takes billions of years. You start with tiny fluctuations, end with massive galaxies. But the progression is slow. Bottom-up structure formation. At 300 million years, galaxies should be small, primitive, mostly gas, few stars, limited structure, nothing like what Webb observed. The galaxies are massive, well-formed, rich in heavy elements. They look billions of years old. But the universe was not billions of years old when they formed. More discoveries followed. JADESGSZ140. Redshift 14.2. Light traveling 13.6 billion years. Formed just 250 million years after the Big Bang. Even more massive than Glass Z13. Even more evolved. The problem intensified. Astronomers call these impossibly early galaxies. Not hyperbole. Genuinely impossible according to current understanding. Structure formation cannot proceed that fast. Not with known physics. Not with measured parameters. The timescales do not work. Some researchers propose solutions within standard cosmology. Maybe dark matter clumps faster than we thought. Maybe gas cooling is more efficient. Maybe massive stars form more easily at high redshift. Adjustments to models, tweaks to parameters. Pushing theory to accommodate observations. But the adjustments seem forced, fine-tuned. Each new discovery requires more tweaking. The theory becomes increasingly contrived. At some point, you stop adjusting and start questioning whether the framework is wrong. Lior Shamir offers alternative explanation. Maybe the galaxies are not as distant as we calculate. Maybe our distance measurements are wrong due to rotation effects. If galaxies are closer, they formed later. More time for structure formation. Problem solved. The evidence fits. If you recalibrate distances, accounting for cosmic rotation, the impossible galaxies become possible. They are still distant, still early, but not impossibly so. The age paradox disappears. Standard structure formation suffices. This is testable. Independent distance measurements using different methods should show whether current estimates are wrong. Gravitational lensing, supernova observations, multiple techniques cross-checking. If they all need similar corrections, the recalibration is real. If they do not, the problem remains. Another possibility comes from bounce cosmology. Maybe the universe is older than we think. Not 13.8 billion years, more like 25 billion years. The bounce happened longer ago. Galaxies had more time to form, but this contradicts radioactive dating. Elements in Earth's crust indicate specific ages. Oldest rocks are roughly 4.5 billion years old. The solar system formed then. Before that, the galaxy existed for billions of years. The timeline seems fixed by nuclear physics, hard to adjust, unless time flows differently in a rotating universe. General relativity permits time dilation. Clocks run at different rates in different gravitational fields. They also run differently in rotating reference frames. Perhaps cosmic rotation creates time dilation effects that make the universe appear younger than it actually is. This sounds like special pleading, ad hoc explanations to save the theory, but the mathematics might work. Rotating space-time has complicated clock synchronization. What one observer measures as time differs from what another measures. Global age becomes ambiguous. The resolution will come from observations. More galaxies at high redshift, more tension with predictions. The universe appears to have been busy forming galaxies far earlier than theory suggests. Either our theory is wrong or our observations are misleading. The stakes are high. If distance measurements need fundamental recalibration, our entire cosmic map is wrong. Galaxy positions, structure formation timelines, expansion history, everything shifts. Decades of accumulated knowledge requires revision. But if the universe truly contains impossibly early galaxies, physics needs new mechanisms. Faster structure formation, different dark matter properties, modified gravity, something beyond the standard model, revolutionary changes to fundamental theory. Either way, something major is wrong with current understanding. The impossible galaxies guarantee that. They exist. We see them. They should not be there. The universe is telling us something important. We just need to figure out what. Chapter 22. The 70-year cover-up. Raj Pathria published his paper in December 1972, Nature magazine, one of the most prestigious journals in science. The title was modest, The Universe as a Black Hole. The content was revolutionary. He calculated that our observable universe has the exact properties expected for the interior of a black hole. The reaction was silence, not dismissal, not controversy, just silence. Other physicists ignored it. Textbooks did not mention it. Reviews overlooked it. The idea disappeared into the literature's vast archive, cited occasionally, never seriously discussed. Forgotten. Why? The mathematics were sound. Pathria was a respected physicist. The journal was legitimate. The idea was testable. Yet the community collectively decided not to engage, not to investigate, not to pursue the implications. The paper became invisible through indifference. This was not conspiracy. No one suppressed the work deliberately. No one forbade discussion. The idea simply seemed too weird, too disconnected from practical questions, too philosophical. Physicists had real problems to solve: particle physics, quantum field theory, solar neutrinos. Black hole cosmology seemed like mathematical curiosity. Interesting, perhaps, but not useful. Then, in the 1990s, Lee Smolin revived the concept. His cosmological natural selection proposal brought black hole universes back to attention. If black holes create universes, physics could evolve through reproduction. The idea was novel, provocative. Science journals covered it. Public interest grew, but the mainstream cosmology community remained dismissive. The theory made no testable predictions about our specific universe, only statistical claims about populations of universes we cannot observe. Philosophy dressed as science, not worth serious attention. Move on to real physics. Nikodem Poplarski's work in the 2010s changed this. He showed that including torsion in general relativity produces bounces automatically. The singularity disappears. Black holes create expanding universes. The mechanism is concrete. The predictions are specific. Testing becomes possible. Still, most cosmologists ignored it. Standard inflation cosmology worked fine. No need for alternatives. The Big Bang model explained observations. Dark energy and dark matter could be worked out eventually. Why abandon successful framework for speculative ideas about living in black holes? The established theory had momentum. Career incentives favored working within it, publishing papers that extended it, not questioning foundations. This is how science actually works, not purely rational evaluation of evidence. Social factors matter. Career pressures matter. Established ideas resist change, even when alternatives have merit. It takes extraordinary evidence to overcome institutional inertia. Black hole cosmology lacked that evidence until recently. James Webb observations might change this. Galaxy rotation asymmetry is hard to ignore. Impossible early galaxies demand explanation. Hubble tension persists despite years of checking. Standard cosmology faces multiple challenges. The cracks are showing. Alternative theories look more attractive. Enrique Gastañaga's recent work provides mathematical rigor. His analytical solutions show bounces are not just possible, but inevitable. The quantum exclusion principle prevents singularities automatically. The cosmological constant emerges naturally. Testable predictions follow. Positive curvature, specific rotation patterns, observable consequences. This combination might finally force the community to engage seriously. Not because the idea is more correct now than in 1972. The mathematics was always valid. But because observations increasingly favor it, anomalies accumulate. Standard explanations seem contrived. Black hole cosmology offers simpler answers. Science progresses through generational change as much as rational persuasion. Thomas Kuhn documented this in his work on scientific revolutions. Old paradigms do not get disproven. They get abandoned when their proponents retire and younger scientists embrace alternatives. Harsh, but realistic. The current generation of cosmologists invested careers in standard inflation cosmology. They wrote textbooks, trained students, built instruments, analyzed data, all assuming Big Bang plus inflation plus dark matter plus dark energy. Admitting this framework might be fundamentally wrong means admitting decades were spent on incomplete understanding, difficult psychologically. Younger researchers face less sunk cost. They can adopt black hole cosmology without abandoning life's work. Some are doing so. Papers appear with increasing frequency. Conferences include sessions on bounce cosmology. The idea gains legitimacy through persistence and accumulating evidence. But resistance remains strong. Peer review often rejects papers on black hole cosmology. Grant applications get denied. Job candidates focusing on it struggle to find positions. The institutional barriers are real, not conspiracy, just normal academic conservatism. Established ideas have advantages. Alternatives must fight for attention. The 70-year delay is not cover-up. It is how science works. Ideas need time to mature. Evidence must accumulate. Community must be convinced. Brilliant insights can be ahead of their time. Pathria was probably right in 1972. But the evidence was insufficient. The theory was underdeveloped. The community was not ready. Now the situation changes. Evidence grows, theory improves, the idea becomes respectable. Within a decade, black hole cosmology might be mainstream, or it might remain fringe. Observations will decide. Science eventually gets it right, just not always quickly. Chapter 23. What inflation really was. Cosmic inflation is cosmology's most successful theory. Proposed in 1980 by Alan Guth, refined by Andrei Linde and others, explains multiple cosmological puzzles: the horizon problem, the flatness problem, the monopole problem, all solved by a brief period of exponential expansion in the first fraction of a second. The horizon problem is this: the cosmic microwave background has the same temperature everywhere, to within 1 part in 100,000. Perfect uniformity. But distant regions of sky have never been in causal contact. Light has not had time to travel between them. So how did they reach the same temperature? How did they communicate? Inflation solves this. Before inflation, the universe was small. All regions were in contact. They equilibrated to uniform temperature. Then inflation exponentially expanded space. Regions that were neighbors became separated by vast distances, but they retained their common temperature. What we see as causally disconnected regions were connected before inflation stretched them apart. The flatness problem is this: the universe appears spatially flat, curvature within 1% of zero, but flat is unstable state. Any small deviation from flatness grows exponentially over time. For the universe to be this flat today, it must have been incredibly flat early on. Absurdly precise initial conditions. Why? Inflation solves this. Exponential expansion flattens space-time automatically. Like inflating a balloon, the surface curves less as it expands. Inflate enough, and any initially curved region becomes approximately flat. The universe appears flat because inflation stretched it flat. The monopole problem is this: grand unified theories predict magnetic monopoles should form in the early universe. Isolated north or south poles. We see none. Not one. Where did they go? Inflation solves this. If monopoles formed before inflation, exponential expansion diluted them to undetectable density. Maybe one monopole in the entire observable universe. Too rare to find. Problem solved. 3 major puzzles. 1 mechanism. Elegant, testable, successful. Inflation became standard cosmology. Textbooks teach it. Observations confirm its predictions. The theory works, but inflation has problems. What is the inflaton field that drives expansion? Never observed. No known particle corresponds to it, just a hypothetical field introduced to make the math work. And the field needs precisely tuned potential energy. Too steep and inflation never starts. Too flat and inflation never ends. The window is narrow. Fine-tuning problem. Bounce cosmology offers alternative. Inflation is not a special phase requiring new fields. It is the natural dynamics of the bounce. When collapse reverses, quantum pressure drives rapid expansion. The same force that stopped the collapse pushes outward exponentially. Automatic inflation. No inflaton needed. The horizon problem is solved differently. Before the bounce, the collapsing cloud was in causal contact throughout. All regions equilibrated. Then the bounce happened. Expansion began. The regions separated, but they retained their common temperature from the collapsed state. Same solution, different mechanism. The flatness problem is solved differently. The bounce naturally produces near-flat geometry. The collapsing cloud has slight curvature. The bounce preserves that curvature. After expansion, the universe appears nearly flat with small positive curvature. Predictions match observations. The monopole problem is solved identically. If monopoles formed before the bounce, rapid expansion afterward diluted them. Same mechanism as standard inflation. Same result. No monopoles observed. So bounce cosmology explains everything inflation explains, without introducing new fields, without fine-tuning potential energy, using only known physics. General relativity plus quantum mechanics. Nothing more. The predictions differ slightly. Standard inflation with a true cosmological constant predicts exact flatness. Bounce cosmology predicts small positive curvature. Measurements will distinguish them. Euclid and other satellites will tell us which is correct within a decade. Another difference involves primordial gravitational waves. Standard inflation produces specific spectrum of gravitational waves from quantum fluctuations during exponential expansion. These waves would imprint patterns in cosmic microwave background polarization. Multiple experiments search for this signal. None found yet. Bounce cosmology predicts different gravitational wave spectrum. The bounce creates unique signature. Quantum fluctuations during maximum compression behave differently than during inflation. The patterns differ detectably. Future observations could distinguish bounce from inflation by measuring gravitational wave properties. This is critical test. If primordial gravitational waves show standard inflation signature, bounce cosmology needs modification. If they show bounce signature, standard inflation faces problems. Clear prediction, definite observation, science at its best. Meanwhile, bounce cosmology is more economical, fewer assumptions, fewer free parameters, more predictive. By scientific standards, preferred over standard inflation unless observations rule it out. Occam's razor favors simpler explanations. Bounce is simpler. The community has not embraced this yet. Standard inflation has 40 years of development, thousands of papers, entire careers built on it. Institutional momentum is enormous. Alternatives need overwhelming evidence to overcome that momentum. Currently, evidence is suggestive but not overwhelming. But the situation could change quickly. One decisive observation, one confirmed prediction unique to bounce cosmology, one failure of standard inflation to explain new data. Any of these could shift opinion. Science can turn on single, crucial measurement. Inflation was our understanding of how the universe began. Bounce cosmology says inflation was how our universe bounced inside a black hole. Same observations, different interpretation, deeper mechanism, more fundamental explanation. Same story told with better understanding of what actually happened. The exponential expansion we call inflation was real. The mechanism was not a mysterious inflaton field. It was quantum pressure, reversing gravitational collapse, the fastest rebound in history. The moment our universe burst into existence from inside something else. Chapter 24. The Arrakis Mission. The European Space Agency will launch Arrakis in approximately 2030. The name comes from the star Mu Draconis. The mission's purpose is measuring ultra-low surface brightness features, faint structures around galaxies, stellar halos, dark matter distributions, things too dim for ordinary telescopes. But Arrakis will do more. Its extraordinary sensitivity to faint signals makes it ideal for testing cosmic curvature. By mapping how light bends around galaxy clusters, it will measure space-time geometry with unprecedented precision. The data will reveal whether the universe is perfectly flat or slightly curved. This matters critically for bounce cosmology. Enrique Gastañaga's theory predicts 0.2% positive curvature, testable, falsifiable. Arrakis has the sensitivity to detect this if it exists. No other planned mission can match its precision for this measurement. The technique uses gravitational lensing. Massive galaxy clusters warp space-time. Light from background galaxies bends around them. The bending depends on cluster mass and space-time curvature. By measuring thousands of lensing events, Arrakis will reconstruct the geometry of space itself. Current measurements constrain curvature to within 1%. Arrakis will achieve 0.1% precision, 10 times better, enough to definitively test the bounce prediction. If curvature exists at predicted levels, Arrakis will find it. If space is flatter than 0.1%, the theory fails. The mission carries a 2.5-meter telescope, enormous for space-based instruments, wide field of view, designed specifically for detecting faint extended structures, 6-year operational lifetime, mapping billions of galaxies, measuring millions of lensing events, unprecedented statistical power. Other missions will contribute. NASA's Nancy Grace Roman Space Telescope launches 2027. Similar goals, different techniques, independent measurements. If both missions detect positive curvature, confidence grows dramatically. Agreement between instruments is crucial for establishing controversial results. Ground-based observatories will help. The Vera C. Rubin Observatory is already operating. Its legacy survey of space and time maps the entire visible sky every few nights. Billions of galaxies. Time domain astronomy, perfect for measuring how cosmic structure evolves. Another independent test of geometry. Combining all these datasets will give definitive answer. Flat universe or curved, positive or negative, large or small. The measurements will be irrefutable. No room for ambiguity, no hiding in uncertainties. Clear result within 10 years. If positive curvature is detected near predicted values, black hole cosmology becomes mainstream, not proven conclusively. Science rarely proves theories absolutely, but strongly supported. The best explanation available, standard cosmology, would need serious revision. If perfect flatness is confirmed, bounce cosmology faces problems. Maybe the curvature is smaller than predicted. Maybe quantum effects during the bounce are more complex. Maybe the theory needs modification. But simple bounce model would be ruled out. Back to drawing board. If negative curvature is detected, both theories fail. Negative curvature suggests different cosmology entirely. Open universe, hyperbolic geometry, radically different from current understanding, would require new physics, new explanations, major revolution. The smart money says flat within 0.1%. Most cosmologists expect this. Standard inflation predicts exactly flat. Measurements trend toward flat. Each improvement finds less curvature. Extrapolating suggests 0 is correct answer, but nature surprises us. Measurements sometimes reveal unexpected results. Predictions fail. Theories need revision. Science advances through these moments. When observation contradicts expectation, when data forces new thinking, Arrakis might deliver such moment. Detection of slight positive curvature would shock the community, force reconsideration of fundamental assumptions, open door for black hole cosmology. Validate decades of work by Patria, Poplawski, Gastañaga, and others. Vindicate the fringe idea, or confirm the mainstream. Perfect flatness supporting standard inflation. Decades of conventional cosmology validated. The universe is what we thought. No bounces. No parent black holes. Just Big Bang plus inflation plus dark matter plus dark energy. Standard model triumphant. Either way, uncertainty ends. The question is answered. We will know whether we live inside a black hole or not. Direct measurement, observable consequence. The speculation becomes settled science. One way or another, the mission is being built now. Engineers designing instruments, technicians assembling components, launch vehicle being prepared. Everything proceeding toward 2030 launch. Barring delays, which always happen, the satellite reaches orbit on schedule. 6 years later, results arrive. By 2037, we will know. The universe will have told us its geometry. That geometry will confirm or refute the bounce. Clear, definitive. No more uncertainty, just answer. And if the answer is positive curvature, everything changes. Our understanding of reality undergoes revolution. Cosmology rewrites itself. Textbooks need new chapters. Students learn different story. The universe becomes stranger and more wonderful than we imagined, because we would know for certain we are living inside a black hole. Chapter 25. Living on the inside. Imagine you are one of those observers in the parent universe. You point your telescope at a black hole, an ordinary collapsed star. Nothing special, just another dark object among billions. You measure its mass, calculate its properties, study Hawking radiation slowly leaking out, standard observations of standard black hole. You have no idea an entire universe exists inside. Trillions of galaxies, quintillions of stars, countless planets, perhaps life, perhaps consciousness, perhaps civilizations wondering about their cosmic origins. All of it hidden behind the event horizon, invisible, inaccessible, unknowable. From your external perspective, the black hole is small. The event horizon spans perhaps hundreds of miles. The mass is finite. The structure is simple. One object in your sky. Nothing mysterious. Physics understood. Equations solved. Just another feature of space-time. But from inside, that tiny region contains infinite possibilities. Billions of light years of space. Billions of years of time. Expansion creating room for complexity. Evolution generating diversity. The interior is vast beyond your comprehension. Yet from outside, it appears as mathematical point. This is our situation. We are the beings inside, experiencing vast, expanding universe, observing distant galaxies, measuring cosmic parameters, developing cosmology, creating theories about our origin, all while trapped in what appears externally as tiny collapsed region. We cannot see out. The event horizon prevents it. Information cannot cross from parent universe to us. We are causally disconnected, isolated. Whatever exists beyond our cosmological horizon is forever inaccessible. We can theorize, we can speculate, we can calculate, but we cannot observe. Does this matter practically? For daily life, no. Physics works identically whether we are in a black hole or not. Stars still burn, planets still orbit, chemistry still functions, biology still evolves, technology still advances. Nothing changes experientially, but philosophically, everything changes. Our cosmic significance shrinks. We are not living in the universe. We are living in a universe, one among uncountable others, each isolated in its own black hole, each unaware of the vast reality beyond its boundaries. The parent universe might be incomprehensibly larger, perhaps infinitely larger. Our entire observable cosmos fits within a tiny collapsed star from their perspective. What seems vast to us is microscopic to them. Scale is relative. Significance is contextual, and their universe might be inside another black hole in a grandparent universe. The nesting could continue infinitely, turtles all the way down, or rather, universes all the way up. Each level, thinking itself fundamental, each level unaware of the hierarchy. This removes the question of ultimate origins. No first cause needed, no creation moment, no beginning of time. Just infinite regress of black holes creating universes, creating black holes. Always has been, always will be. Eternal existence without foundation. Some find this disturbing. Infinite regress seems unsatisfying. We want ground floor, fundamental level, bottom of the stack, something that exists necessarily rather than contingently. But maybe reality has no such level. Maybe existence is fractal, self-similar at all scales, no privileged layer. Others find it liberating. No need to explain why something exists rather than nothing. Existence is necessary. Reality is infinite. The question dissolves. Philosophy becomes simpler. Just accept what is and explore its structure. Practically, we continue as before. Measure the universe, test theories, build instruments, analyze data, learn how our cosmos works. Whether we are in a black hole or not, the scientific method applies identically. Observations constrain theories. Experiments test predictions. Knowledge accumulates, but the metaphysical implications are profound. If we are in a black hole, then other universes exist beyond our reach. Life might have evolved in many of them. Intelligence might be common. Civilizations might thrive. All invisible to us, all unreachable, all developing their own understanding of reality. We will never meet them, never communicate, never share knowledge. The event horizon is absolute barrier. No technology can cross it. No signal can penetrate. We are alone by geometry, isolated by the structure of space-time itself, yet we share common origin. All universes emerged from black hole bounces. All experienced similar expansion. All developed structure through gravitational collapse. All followed same physical laws. We are siblings separated at birth, family divided by impassable boundaries. This is what living on the inside means. Vast experience of space and time, rich complexity of structure, but ultimate limitation of scope. We can know our universe thoroughly. We can map every galaxy, measure every parameter, understand every process, but we can never know what lies beyond. The parent universe remains forever mystery. Unless we are wrong, unless Bounce cosmology fails observational tests, unless the universe is not inside a black hole, then our cosmic significance might be larger. We might be the universe, the only one, special, central, unique. But if the measurements confirm positive curvature, if galaxy rotation asymmetry persists, if all evidence points toward the bounce, then we accept our place, inside, limited, one among many, not special, just another pocket of reality carved out by gravitational collapse. Living on the Inside, Chapter 26. The cycle that never ends. Nothing begins, nothing ends, only transitions. Our universe emerged from collapsed matter in a parent universe. That parent universe emerged from a grandparent. The grandparent from a great-grandparent. No, start to the chain. Just eternal sequence of black holes creating universes creating black holes. Or perhaps a cycle. Maybe our universe will eventually collapse. All matter pulled back together by gravity. A big crunch. Everything compressed to maximum density, then bouncing again. Creating a new universe from old one. Phoenix cosmology. Death and rebirth. Current observations suggest our universe expands forever. Dark energy accelerates expansion. Galaxies recede. Space stretches. Eventually, atoms themselves tear apart. Protons decay. Black holes evaporate. Heat death. The cosmos ends in cold darkness. No collapse. No cycle. Just endless dissipation. But Bounce cosmology changes this. If dark energy comes from residual torsion, it might eventually weaken. Billions of years from now. Trillions. Eventually, gravity might overcome expansion. The universe could reverse, begin contracting, all matter falling back together toward another bounce. This creates eternal cycle. Expansion, contraction, bounce, expansion again. Each cycle slightly different. Quantum fluctuations alter initial conditions. Physical constants shift minutely. The universe explores different configurations, infinite variations across infinite time. In this scenario, asking about the universe's age becomes meaningless. How old is something that cycles eternally? The current expansion phase began 13.8 billion years ago, but the previous contraction phase lasted unknown time, and the expansion before that, and so on forever in both directions. Time becomes cyclical rather than linear, not moving from past to future toward end, looping endlessly, each cycle complete in itself, yet connected to all others. The universe has no beginning because there is no first cycle, no end because cycles continue forever. This resolves the fine-tuning problem differently than anthropic reasoning. Why do physical constants have values compatible with structure formation? Not because we exist to observe them, not because we are selected from infinite universes, because the cycle evolves towards stable configurations. Unstable universes collapse quickly. Stable ones persist longer. Over infinite cycles, stability dominates. Natural selection of universes through bouncing. The cosmos optimizes itself through trial and error. Each cycle tests new parameters. Successful combinations persist. Failures collapse rapidly. Over infinite time, the universe converges on physics that produces complexity. We observe finely tuned constants because we live in a successful universe, one that has persisted through many cycles, one that will continue persisting. The alternative universes failed quickly, never developed structure, never formed stars or galaxies or life, never questioned their existence. But our universe works. Stars form, heavy elements synthesize, planets coalesce, chemistry becomes complex, life emerges, intelligence develops, consciousness ponders origins, and discovers it is living inside eternal cycle of collapse and expansion, one iteration among infinite others, neither first nor last. Just now, Roger Penrose has proposed similar idea called conformal cyclic cosmology. Each universe ends in heat death. All mass energy converts to radiation. In infinite future, radiation becomes smooth and featureless. Geometry becomes scale-free. This end state matches initial conditions for new Big Bang. The cycle continues. Penrose's version is different from bounce cosmology. No black holes involved, no parent universes, just single cosmos cycling through infinite phases. But the philosophy is similar. No beginning, no end, just eternal transformation. Which is correct? Current observations cannot distinguish. Both predict similar cosmic history for our current phase. Both explain fine-tuning through cyclic selection. Both avoid the singularity problem. Future measurements might differentiate them, or both might be partially right. Reality combining elements of each. The profound implication is timelessness. If the universe cycles eternally, time is not fundamental property of reality, just a coordinate describing local evolution. Cycles have duration, but the cycle itself is eternal, exists outside time, or rather, contains all time without being limited by it. This matches some interpretations of quantum mechanics. The wave function is timeless. Evolution operators move through time, but the full state exists timelessly. Past, present, future are all equally real, just different coordinates in unchanging mathematical structure. Applied to cosmology, this means our entire history, past and future, exists timelessly. The bounce that created us, the expansion we experience, the eventual fate billions of years hence. All of it is eternal present, laid out in block space-time. We move through it, experiencing time, but the structure itself is timeless. This is philosophical rather than scientific, not testable directly, but it follows from the mathematics. General relativity treats time as coordinate like space. The four-dimensional space-time geometry is what exists fundamentally. Motion through time is illusion created by conscious observers. If true, then asking when the universe began is like asking where space begins. Meaningless question. Space and time are part of structure, not independent of it. The universe does not exist in time. Time exists in the universe. The cosmos is, was, will be, all simultaneously, eternal, unchanging, complete. We are patterns in that eternal structure, transient configurations of matter and energy. existing briefly in cosmic time, experiencing flow from past to future. But from outside time, if such perspective makes sense, we simply are, along with everything else, past civilizations, future civilizations, all existing in timeless now. This is the cycle that never ends, not because it runs forever into future, but because it has no beginning or end, just is, eternal existence, infinite complexity, boundless possibility, reality in its fullest expression, and we are part of it, living inside a black hole that bounced from previous universe, experiencing expansion that might lead to another bounce. One cycle in infinite sequence, one universe among infinite others. Brief, local, limited, but real, meaningful, significant despite insignificance. This is what the evidence suggests. This is where the mathematics leads. This is reality if we are brave enough to accept it. We do actually live inside a black hole. The universe is bigger and stranger than we ever imagined, and the journey to understanding has only begun.